Hello wonderful person, this is Anton, and yeah, I'm on some other planet right now. Anyway, super quick announcement. I'm just going to be taking a short break because my voice is actually not doing so well, and I'm still recovering from a relatively long cold. So in the meanwhile, enjoy some of the older videos and some of the new compilations, including this one right now that's going to be focusing on dark matter, dark energy, and a lot of other mysteries. See you soon. So in the last few months, because of discoveries from the James Webb Space Telescope, along with some of the most advanced radio telescopes, there have been quite a lot of discoveries about mysterious dark matter. This strange phenomenon we know exists, but whose origin is still not entirely understood. The phenomenon responsible for holding galaxies together and for also forming a lot of gravitational anomalies across the entire universe. Most visible as beautiful gravitational lenses in a lot of different locations. And so quite a few recent studies investigated dark matter from different perspectives, discovering a lot of exciting things we didn't know before, but also discovering certain things that might be pointing at something we still don't understand, or even pointing at our ideas or theories maybe not being entirely correct, which is of course expected because this is still a developing field. And so even though I kind of wanted to make this into one long video at first, I realized that there's just way too much to discuss. So we're going to break this into maybe several parts. In this first video, we're going to discuss some of the recent discoveries that really kind of surprise us to some extent, helping the scientists confirm certain predictions and helping reveal certain things about dark matter that we originally thought was true. And in the next video, possibly sometimes next week, we'll discuss some of the more controversial discoveries or discoveries that just don't make sense yet. With pretty much all of this coming either from the James Webb Space Telescope, the China's FAST telescope, the largest radio telescope we have right now, or from the iconic Atacama Desert ALMA, all of which have been making incredible detailed observations of the entire universe around us. Although despite all of these observations, the measurements and the explanations are still not super precise, so there's always a chance for an error. Either way though, a lot of observations point at the existence of this invisible matter that seems to act on the universe in quite significant ways. There's really no other way to explain it right now. And quite a lot of these observations are based on what's known as gravitational lensing. Essentially, the bending of the light as the light from a distant bright object, such as a quasar, passes in front of something invisible on the way to planet Earth. In many cases, it is some kind of a galaxy, and you actually see stars or even quite a lot of gas in the region in front of this quasar. As a matter of fact, if it is gas, you can even tell by the light coming from the quasar because certain types of frequencies are going to be interacting with the gas and creating a certain types of spectrum. But sometimes, the light arriving to us that's gravitational lensed seems to be lensed by something completely invisible, yet still really massive. And that's of course where dark matter is the only explanation we have. Currently, there is no accepted explanation for what exactly it's made out of, but a lot of scientists believe that it's probably some kind of a very light, slow-moving particle that seems to only interact with things gravitationally and not in any other way. Some of the videos in the description clarify these ideas a little bit more. And so some of the scientists using the famous Atacama Large Millimeter Array, or ALMA, have recently analyzed a lot of gravitational lensing systems, specifically focusing on the system of MGJ0414, a massive galaxy distorting the light from a distant quasar that seems to be about 11 billion light-years away from us. And intriguingly, inside this image, they found some strange anomalies, visualized as these unusual patches you see in the image. And these actually represent unusual chunks of what appears to be massive invisible objects, or fluctuations in gravitational lensing, with each of them being less than 30,000 light-years across. In other words, they could be very tiny, very massive galaxies that don't seem to possess a lot of stars or actually any stars and seem to be made out of just pure gas. But in this case, even this gas does not seem to change the light coming from the quasar at all, implying that it's basically invisible chunks of invisible matter, or for the lack of better words, dark matter chunks. Very thick concentrations of dark matter that seem to produce additional gravitational lensing effects. Because without these unusual chunks, the image of the quasar was predicted to look very different. Basically here, the modeling and the actual observations don't really match. But these unusual fluctuations, or these unusual concentrations of small, really dense, invisible matter, explain the observations really well. And though I guess obviously it could be maybe some kind of a large concentration of black holes, with many of them forming some kind of a very large cluster, because of the total amount of mass here and the volume of thousands of light years, this would require a huge amount of black holes that would just not make a lot of sense. And we would also expect some of these black holes to produce other observations as well. And so here, whatever this is, it truly seems to be invisible. No stars, no gas, nothing else. Just unusual density of invisible matter. And though this might sound weird and unusual, it's actually really not, because that's exactly what modern dark matter theories predict about the distribution of dark matter clumps across various galaxies. As a matter of fact, this seems to fit the prediction extremely well, with many previous theories explaining the existence of these chunks across various intergalactic regions. But more interestingly, this was not the only such object discovered in the last few months. In other words, another recent observation found something very similar using completely different techniques and completely different telescopes. And in this case, this object even has a name now. It's referred to as Cloud 9. It seems to be located much closer to us, near the famous galaxy M94, the galaxy that sort of looks like this, but it does not seem to be part of the galaxy and is just in the same region. And well, in this case, it's actually a slightly different object, because here there was a detection of hydrogen, but absolutely no stars. In other words, this is actually a combination of invisible matter and a lot of neutral hydrogen. But there are no stars here, or at least not invisible, making this an invisible massive object. And turns out that once again, this sort of is a predicted idea. These might be known as reionization-limited HI clouds, relics, a type of a dark matter halo that doesn't contain any stars. And in this case, this is actually a really exciting discovery, because in some sense, it shows us how many galaxies might have formed in the early universe. When it comes to the formation of early galaxies, it's always been believed that many of them started in regions of space where there was a much higher concentration of dark matter, representing a kind of a dark matter chunk. And eventually, a lot of these dark matter halos collapse, forming large, thick formations with a lot of gas falling in as well, basically forming baby galaxies. This has always been the main prediction of how early galaxies formed across the universe, and how dark matter halos most likely started all of this. But a lot of these early predictions and a lot of these models have also predicted the existence of some of these halos that never truly collapsed to the end and never actually formed into real galaxies, representing a kind of a failure. So basically, dark matter halos with no stars, just some leftover primordial gas. Yet to date, none of these objects have ever been found, despite a lot of different theories claiming that they should exist. And while quite a lot of studies seem to imply that maybe this particular discovery is exactly that. This Cloud 9 might really be this primordial halo that never became a galaxy. And what's even more exciting is the distance. It seems to be only about 18 million light years away from us. This is basically galactic neighborhood, with the last exciting discovery coming from something that's even bigger and even more mysterious: the ancient quasars, the brightest objects in the universe, which represent active galaxies with very massive black holes that produce enormous amount of light and radiation because of tremendously large accretion disks. And intriguingly enough, there's always been a very unusual relationship between a typical quasar and its apparent mass of its dark matter halo. Or just to rephrase this, many quasars we've discovered so far, and these are usually really easy to find, surprisingly seem to have a somewhat similar relationship when it comes to the total mass of the dark matter halo around them. These halos are known to exist around most galaxies out there, and they're essentially what's holding the galaxy together. But for a lot of these quasars, a typical mass of the halo seems to be somewhat constant, approximately 10 trillion times the mass of our Sun. And it seems to be constant independent of where the quasar is located. And this has been generally established by measuring the orbital velocities of nearby galaxies and by looking at hundreds and hundreds of different quasars. And so it looks like most quasars have a somewhat constant mass of dark matter halo. even if you look at quasars really far away, billions of light years away from us, or the ones much closer. All of them seem to have had these halos, but also that maybe these halos are responsible for the quasar formation. Or in other words, there seems to be a certain mass of a dark matter halo that actually activates a galaxy to possibly become a quasar, independent of how old the galaxy is. Which implies that the gravitational influence from the halo of dark matter around the galaxy basically increases the amount of gas falling into the black hole, thus activating the galaxy and making black holes suddenly consume a lot of mass, usually at least 10 solar masses per year. And so in a recent study, by looking at 107 different quasars at a redshift of about 6, the scientists discovered that the mass here seems to be relatively constant. Not the mass of the galaxy, the mass of the dark matter halo. This once again was discovered by looking at various galaxies moving around the quasar and measuring the total mass of the entire cluster. In this case, of course, implying that the dark matter halo itself seems to play an important role in activating supermassive black holes in the middle of various galaxies, which by itself is a pretty big discovery. It might finally help us understand how exactly quasars form and what basically drives the evolution of various galaxies across the universe. But despite these very unusual, exciting discoveries in regards to dark matter, we did have some additional discoveries that seem to create a few problems, such as unusual distribution that does not match predictions, and also discoveries from the cluster known as El Gordo, which seem to also violate certain predictions of modern cosmology. And we'll talk about all of this in the next video that should be out sometimes next week or maybe in a few days from now. So if you want to learn more about this, subscribe, share this with someone who loves learning about space and sciences, come back tomorrow to learn something else, support this channel on Patreon by joining the channel membership or by buying the Wonderful Person t-shirt you can find in the description. Stay wonderful, I'll see you tomorrow, and as always, bye bye. So not so long ago, we've discussed recent discoveries, and actually really exciting discoveries, in regards to the mysterious phenomenon known as the dark matter. You can learn more about all of this in one of the videos in the description, but it basically included things like unusual chunks of dark matter pretty much in the middle of nowhere, you can sort of see them visible right here, and even chunks of undeveloped galaxies that were essentially made out of dark matter for the most part, but contained a few stars and a lot of underdeveloped gas. But in that video I also mentioned that there were some discoveries that basically presented us with a few mysteries, and more specifically, a few unresolved problems when it comes to the idea of dark matter as an invisible particle. And so in this video we're actually going to touch on some of these ideas and discuss some of these new observations, including several observations that actually have no explanations even today, and some observations that have been established to be a major problem that potentially have one explanation that is being tested right now. And so, hello wonderful person, this is Anton. Let's discuss dark matter once again, but this time focus on some of the major problems. And specifically various problems that have been established through the collection of data in regards to what's known as the clumpiness of the universe, and in regards to the formation of very large clusters that usually form the largest collections of dark matter in the local universe. And let's start with the first problem. It's actually technically now known as the tension, or a new cosmological tension, the most famous tension being the Hubble tension, or the problem with the expansion of the universe. You can learn more about this in some of the videos in the description, but this new tension is known as S8 tension, or Sigma 8 tension. It sort of refers to something nobody expected was even a problem until recently. Here the problem is the overall clumpiness of the entire universe. Or basically, how concentrated things are if you were to observe them from a distance. Obviously, if something is very clumpy, it's going to appear more web-like. If something is less clumpy, it's just going to be more spread out. And a lot of previous observations, and actually a lot of previous calculations, mostly based on the observations and calculations from the cosmic microwave background, produced an overall value for this clumpiness established to be approximately 0.83. This was calculated and recalculated many times, and so it was always assumed to be a constant. It's even part of an important formula in various cosmological studies. But by using more recent data, especially from the Dark Energy and Geometry of Space Survey, also known as BOSS, Baryon Oscillation Spectroscopic Survey, recent studies used positions of approximately 1 million nearby galaxies to recalculate the overall clumpiness near us, and then compare the clumpiness from today to the clumpiness from back then. This was supposed to show us how things changed over time, and the original prediction was always that it's most likely going to change a little bit, but it's probably going to be more clumpy, possibly by just a little bit, because as the time goes by, overall, galaxies and a lot of other objects tend to cluster together despite the universe expanding over time. But instead, the initial results were the opposite. And that was kind of strange. So additional teams joined in and tried to rediscover what's going on here. And so this time by using 25 million galaxies, with some of them billions of light years away from us, all of their results confirmed once again that the clumpiness today seems to be lower than back in the days. The average was about 0.76, almost 10% lower instead of being higher compared to what we see in the cosmic microwave background. And because the idea of clumpiness is the fundamental property of the standard model of universe we use today, not understanding why it seems to be so different actually is creating a bit of a problem, or more like a big problem. These initial discoveries make it somewhat unclear why this is so or what's happening here, and actually creates a major challenge for most of the theories involving things like, for example, large particles known as WIMPs that some scientists believe are responsible for dark matter. Because previous predictions always suggested that things are going to be more clumpy over time. We see the opposite. But several studies started to propose additional explanations and actually even came up with something that currently makes sense. And it doesn't break any theories. This is actually something involving axions. The unusual particles we believe exist that could be responsible for dark matter as well, but were originally proposed as an explanation for the idea of existence of matter over antimatter. These particles might be responsible for the production of more regular matter that you and I are made out of. And so by performing analysis on various gravitational lenses, especially the ones coming from distant quasars, and trying to recreate what kind of a dark matter would be responsible for these specific images, some of the scientists started to propose that maybe it's actually axions here and not so much anything else. With additional simulations that produce the universe with or without axions, basically revealing something very similar. If the universe does not contain axions and contains heavier particles such as WIMPs, representing dark matter, the universe just doesn't look the same and is extremely clumpy, but also very different from what we observe in real life. Yet if you replace everything with axions, which in comparison are believed to be extremely minuscule and very low in mass, actually almost acting like waves instead of particles, the clumpiness drops dramatically, the universe becomes very similar to what it really is, and most importantly, this whole tension thing kind of disappears. And this concept is sometimes referred to as the fuzzy, cold dark matter, where basically dark matter is not really a particle and much more of a wave now, has been described in a previous paper in the video in the description, with a lot of these axions potentially having wavelengths even larger than entire galaxies, and thus influencing formation and distribution of dark matter in very different ways compared to a more massive invisible particle. But these explanations are of course nice and interesting. Is there actually any proof though? Well, at the moment there isn't, but it might be coming soon. So first of all, there are two potential ways of discovering if this is true or not. One of them involves the sun. And here the assumption is that maybe some of these particles might get stuck inside the sun, stay there for a while, and then get annihilated, forming certain particles, including neutrinos, of a very specific high energy. And if we find them coming from the sun at any point, it would confirm the existence of certain types of dark matter. Although at the moment nothing like this has been discovered in the last few years. And so nothing coming from the sun just yet. There is, however, a much more intriguing experiment that actually started not so long ago, ALPS 2, which involves a long, over 100-meter long laser that's going to be directly looking for axion using their fundamental property. That property being the fact that they actually change into photons in presence of very powerful magnetic fields, but only sometimes, actually extremely rarely. So rarely, as a matter of fact, that this experiment is going to be running for years before anything could be discovered. But the way it works is pretty simple. A laser is going to be firing inside a relatively long tube that's lined up with very powerful magnets. Because laser is made out of photons, the idea here is that maybe sometimes some of these photons are going to reconvert back into axions. And because this laser is currently firing at nothing but the wall, if these axions are formed at any point, they're going to pass through this wall and reach the next point of the experiment. More magnets. And at that point, one of these axions, if the theory is correct, is going to reconvert back into the same type of light. So basically it's like shining light through a very thick wall. But obviously just a few photons getting through the process of conversion into axions and back into light. And the theory here is very solid, so it's just a matter of time now to see if there are going to be any results. And if confirmed, this basically solves a lot of problems in modern physics, including of course the problems of matter and antimatter. Although interestingly enough, just a few years ago, there was a potential detection of these axions coming from very powerful magnetic fields near extremely well-known neutron stars. You can actually learn more about this in the description below. But in that case, it could actually be explained in some other ways. In this experiment, detecting light coming through the wall has absolutely no other explanation. It could only be converted axions, which would then explain the clumpiness of the universe, the unusual observations from various quasars, and prevent us from having a new type of attention. But yeah, there's probably going to be years of research before anything is going to be achieved. But despite this particular idea having some explanations, there's one concept that's still impossible to explain even right now, and it's actually based on recent observations from very large galactic clusters, usually on the collision cores. The most famous in this case is El Gordo, the colliding cluster that's sort of visible right here, in this case showing us the interaction of different particles producing X-rays. In reality though, the cluster itself is somewhat difficult to see, but there's definitely a lot of mass here, although that's not really the problem. The problem is the fact that this cluster is really far away from us, so something like 8 billion light years away from planet Earth, suggesting that it existed way too early compared to what we expect from galactic development. Normally, scientists assume that galaxies start to grow larger and larger and combine into clusters, which then eventually start colliding, and this process should take billions of years. And this is something that we expect in modern universe, not in a universe when it was approximately half its age. So this collision just seems to have happened way too soon. But there is maybe one potential explanation. Everything here could work if things were actually moving much faster, and if the collision was happening much more quickly. So technically El Gordo can be recreated if things are moving way faster, at a very high speed. In this case, the proposed velocity was approximately 2300 km per second, much faster than expected from galaxies at this point in time, or from galactic clusters in general. And though it is possible, it's just extremely unlikely, creating a problem for ideas of dark matter because it shouldn't allow things to move that fast that early on. And though at the moment it's kind of difficult to explain it for this cluster, a very similar issue exists in a much closer and a more well-known cluster we usually refer to as the bullet cluster. Here the problem is very similar. Things are moving too fast and colliding a little bit too early on compared to a lot of other galaxies. And so exactly what's happening here, that's not something we're going to know until someone figures it out. At the moment there's really no model, no explanation, nothing we have right now that seems to make sense. And because these observations were also confirmed recently with the James Webb Space Telescope, it more or less confirms that there is a mystery to be solved and nobody knows how to approach it just yet. Hello wonderful person, this is Anton, and today we're going to be talking about the expansion of the universe, or the concept known as dark energy. And actually one of the recent studies that makes a pretty intriguing proposition, which unfortunately we currently are unable to test, because we don't really know much about dark energy to begin with. But the proposition suggesting that in the next few hundreds of millions of years, or even sooner, the universe might actually start to decelerate and eventually even contract. And potentially even contract to the point where it basically shrinks into the infinity once again, restarting the entire process once again. But before I explain more, you also have to remember that a lot of this currently is extremely hypothetical and theoretical. In essence, almost none of this is currently provable based on the observations we have around the universe. There's just not enough data available to say if this is correct or not. But mathematically, it does make sense. But first, let's start with some of the basics in regards to the expansion of the universe, and I guess in regards to the timeline as well. With this image right here, giving us a basic idea of where everything is on this timeline. So roughly around 13.8 billion years ago, that's when the Big Bang began. The universe came to be, increasing in size quite dramatically. This period is known as the inflation, and it lasted for just a fraction of a second. And the amount of expansion during this period is actually kind of mind-blowing. It's been compared to taking a single DNA molecule and expanding it to over approximately 10 light years in length in just a tiny fraction of a second. And that's the basics of the so-called inflation theory. But why this happened, and I guess how this happened, is still unknown today. This theory was actually postulated based on the observations of the primordial light. Then the universe started to expand a little bit slower, with all of this lasting for roughly around 7.7 billion years. And something else happened right at that time. For some reason, the universe then started to accelerate its expansion. In other words, everything in the universe started to move away from each other faster and faster. And that's actually something that came as a complete surprise to scientists back in 1998. According to all of the theories prior to this, the universe was actually expected to slowly decelerate, mostly because of the gravitational attraction of various types of matter in the universe. But there were two very specific projects, the Supernova Cosmology Project and the High-Z Supernova Search Team, that used the data from a lot of different Type 1a supernova from around the universe to discover that for some reason the universe was actually expanding faster and faster the farther in the universe you look. Something that seems to have begun approximately 5 billion years ago. And because of this discovery and because of the propositions made in 1998, the scientists behind all of these studies ended up winning the Nobel Prize. But since then, these discoveries created a lot more questions than provided answers. With one major question, of course, being, what exactly is causing all of this? And is this something that's going to be going on for a very long time? And is this going to be the reason why the universe eventually ends? Is it going to, at some point, expand so fast that it actually rips apart? The hypothetical end scenario for the universe known as the Big Rip. Well, technically this is where the facts end and hypothesizing begins, because mostly everything after this is simply theoretical and currently has no physical proof. There are some proofs for certain ideas, but pretty much everything you hear about the end of the universe after this is usually based on mathematical concepts without actual physical proof provided anywhere. Although before I go on, I actually wanted to also show you this image that's often presented when discussing the idea of expansion of the universe, because there are often misconceptions about what the expansion actually means. In this case, we have to remember that when we say expansion of the universe, it's not really expanding into anything, and it doesn't require anything outside of this space to exist. In other words, there's no actual wall, there's no edge of any kind, it's not really touching anything on the outskirts. But the space-time itself, the stuff we're in, is expanding itself. So in other words, 2 points of space-time are actually going to be farther apart in the next few billion years from now. Which also means that our galaxy right here, in approximately 1 trillion years, is not going to have any neighbors anymore. As a matter of fact, if you're still around and if the universe is still around in 1 trillion years, which we're not sure about, there's not going to be anything in the night skies resembling any galaxy. The concept of a galaxy is going to be gone forever. And I've talked about this in one of the older videos about what all of this might look like in 1 trillion years, somewhere right there, or in a description. But the principle here is really simple. Everything around us is moving farther and farther and farther apart, and at some point, the galaxies are all going to be beyond the observable universe. At this point, if there's any sort of species living on some alien planet, they're not going to even know what galaxies are. Which always made me wonder, has there ever been something in the past, something that is no longer visible to us, something that maybe ancient aliens somewhere out there knew existed, but we cannot possibly even imagine because it's just beyond the observable universe? Once again, another hypothetical concept, nothing we can prove definitively. But there's always been attempts to try to explain the expansion of the universe and the idea of dark energy. For example, there are models such as the back reaction conjecture proposed by Sixi Rasanen that suggest that maybe we're just in a very special region of the universe where everything seems to expand a little bit faster, and so we think that things are accelerating. Maybe we're just in a very special region of the universe where for one reason or another things move a little bit faster. Or maybe it's actually an illusion. Maybe there is no dark energy and there is no acceleration of the expansion, and it's all basically just a bias in all of the data we've collected over the past few decades. And although it is a possible explanation, a lot of recent data suggests otherwise. It does suggest that something is actually causing the acceleration. But the most popular explanation of all of this is actually from the Einstein's equations, specifically Einstein field equations, where there is a constant known as the cosmological constant that suggests that all of this is actually in the fabric of space-time itself. In other words, it suggests that dark energy can never change, and the universe should always be expanding or even accelerating its expansion no matter when or where you are. So basically, it's as if it's part of the equation that's everywhere around us, which would also not really require any particle or any other explanation. But that's not really something we can prove right now, and also a lot of data suggests otherwise. There have been suggestions that cosmological constant might actually be not a constant at all. We've discussed this in some of the previous videos right there or in the description. And so there are quite a lot of alternative explanations to all of this. And one of the more interesting ones involves something known as quintessence, with the word quintessence simply meaning fifth matter, matter number 5. And that's a proposition for an existence of a kind of a particle of dark energy that is not a constant and whose density and whose properties do change with time. And so instead of being a constant in the equation of spacetime, it's literally a kind of a substance that seems to transform depending on the concentration and depending on the density. And in case you're wondering why it's called quintessence or fifth matter, it's because today in physics, the scientists generally believe that the 4 other matters are, well, dark matter of course, the more mysterious one, but also the stuff we made from, which is the baryonic matter, the neutrinos, and of course all of the energy or light around us. With that 5th stuff being quintessence or dark energy. And so the theoretical physicists behind this paper wanted to see if they can crunch some numbers and figure out what could possibly happen to quintessence with time depending on its properties. And first of all, the scientists who do subscribe to this idea usually mention that depending on the ratio of quintessence in the universe, it will become either attractive or repulsive. And generally it's believed that it became repulsive approximately 10 billion years ago, or about 3.5 billion years after the Big Bang. In other words, if you were to look at this again, it really became repulsive somewhere around this time. And even though it's been expanding our universe for billions of years, the calculations in this paper suggest that it actually might be weakening in its repulsive forces. And in the most extreme case, in 65 million years from now, the acceleration of the universe could actually end completely. With quintessence then changing its properties and, instead of being repulsive, now becoming attractive. And following this, about 165 million years from now,
the universe could stop expanding completely and instead would enter a slow contraction era, which, depending on what happens to Quintessence afterwards, might end the universe completely in just a few billion years. In other words, it might actually start contracting to the point where it returns back to singularity, at least from the preliminary calculations. And this could obviously lead to what's known as the Big Crunch, where everything sort of contracts back into a very hot mass and eventually disappears. Or it could lead to that other idea proposed by several scientists, including Roger Penrose, the idea behind the Big Bounce. The universe might bounce back and create a completely new universe after that, essentially restarting the cycle in the process. So that's of course where nobody really knows what's going to happen just yet, simply because we just lack observational data. But I guess what's sort of surprising from these calculations in this paper is how quickly all of this might happen. 65 million years from now is really not that far when it comes to cosmology. As a matter of fact, 65 million years ago, that's when the dinosaur rock go boom killed dinosaurs. So definitely relatively short in cosmological terms. But none of this is provable or disprovable. Mathematically, it's there and it sort of makes sense, but sometimes math and physics do not actually align. A good example I made in one of the previous videos is that in theory, in mathematical theory, you could travel faster than light and then travel back in time. That's the video about time travel, somewhere right there or in the description. But in physics we know that it's impossible, and any kind of a time travel faster than light violates a lot of different physics, making it something that can never be achieved no matter what. And because a lot of things in this model depend on the idea of dark energy already being a poorly understood, poorly explained concept, in that sense it's more a hypothetical scenario than anything else. But for the physicists that do like the idea of quintessence, this particular paper actually does discover some really interesting ideas, such as, for example, that dark energy or quintessence can decay with time. And at some point through this decay, it might start acting like typical matter instead of repulsive matter. And after just a few billion years, the universe is actually going to contract by about half. It's going to shrink more and more with time, suggesting that all of this can change pretty quickly and escalate quite dramatically within just a billion years or so. So quite a unique proposition and quite an interesting paper. But what exactly is happening with the universe and what exactly is happening with dark energy is probably a question we're not going to be answering for the next few years at least, possibly even a few decades. At the moment there's just not enough data collected by various telescopes, and there's really not enough data from the most distant parts of the universe in order to figure out where the universe is headed and what exactly is this dark energy, if it even exists.
A few months ago, we've discussed the launch of the ESA's Euclid telescope, the incredible new telescope designed specifically to answer the biggest mysteries of the universe. It's going to be studying what's known as the dark universe, or basically dark energy and dark matter. And so in that video from just a few months ago, which as always you can find in the description, we've discussed how the telescope is going to be doing all of this, why it's a sort of important mission, and why it has a chance to completely transform our entire understanding of cosmology in the next 6 years. But just a few hours ago, the telescope officially began its mission. The researchers released 5 separate images from various distances away from planet Earth, showcasing how extremely powerful this telescope is, and showing us its abilities, discovering a few things in the process. And so, hello wonderful person, this is Anton. Let's discuss Euclid telescope once again, talk about these 5 pictures, and of course talk about some of these discoveries. Although at the moment this is still very preliminary. Anyway, to start I actually just wanted to once again mention why this telescope is so powerful. First of all, the way it functions is essentially by scanning the sky just once, and while it's doing this, it's able to directly collect a tremendous amount of information about every single object it looks at. And that's because it actually observes everything in several different frequencies, specifically in different frequencies of visible light and near-infrared light. And while doing this, by just taking a look at the object for a little bit, it's able to produce a super sharp visible image over a very large portion of the night skies at the same time. And that's because it uses a wide-angle camera as opposed to other telescopes, such as for example the iconic Hubble telescope, which normally have much higher resolution and are able to zoom in much more,
but do not have an ability to see everything all at once. And so here the point is going to be not to study distant, invisible galaxies or objects that are extremely far away from us, but instead to try to study almost everything all at once, with the main focus being various cosmic structures and various galaxies up to the redshift of about 2, or essentially looking back in time approximately 10 billion years. And then by measuring the redshift of various galaxies and using the phenomenon known as gravitational lensing, it's going to try to assess the amount of dark matter in a lot of parts of the universe, as well as calculate the expansion rate of the universe by comparing the shapes of various galaxies with their redshift. You can learn a little bit more about this from one of the videos in the description, but in essence, it's just going to focus on improving our accuracy and most importantly, on collecting a huge amount of data from approximately 10 billion different objects. Yeah, that's 10 billion. Eventually allowing us to create the largest three-dimensional map of the universe up to the redshift of 2. Hopefully discovering a lot of mysteries about dark matter and dark energy in the process, and potentially discovering a lot of other mysteries as well. But right now this telescope is right here in the L2 Lagrange point, sharing its orbit with the Gaia telescope and with the James Webb. So we basically now have 3 active telescopes in this particular location, all doing absolutely incredible science. And though the early images we received a few months ago were basically just testing if everything works, and it seems to work just fine, the new images that were just released show us how extremely powerful this telescope really is. And so let's briefly discuss these images. The thing is, it's nothing that you didn't know before, but it just looks so much better. And let's start with this. Now this is a crazy image. There's just so much stuff going on here. And as you can probably tell from the image, this is essentially a galactic cluster. And specifically this is known as the Perseus cluster, approximately 240 million light years away from us, very likely containing thousands of galaxies. Essentially representing one of these many clusters forming a much larger supercluster in our vicinity, in this case containing roughly around 1,000 galaxies. But just as a comparison, here's roughly what it looks like with a regular telescope from right here on planet Earth. So yeah, definitely very different. But based on observations in the X-rays, we know there is so much going on in this cluster, because that's exactly what you can see right here. This is a combination of visible light, ultraviolet, and of course X-rays. And so getting a better picture of this cluster was of course important. And just look at how much stuff there is here. Now I'm gonna try to zoom in a little bit, but essentially, by taking this image, the scientists discovered hundreds of thousands of galaxies behind it that we've never seen ever before. And some of them are as far away as redshift of 2. Basically, some of them are 10 billion years old. And what made this particular image at first a little bit unusual is that there was an unusual detection of extra low light coming from the cluster's vicinity, not from the cluster itself. And it was because of this image, it was then discovered that the source of this light seems to be various leftovers from collisions between various galaxies in the cluster itself. And more specifically, from a lot of stars in the intergalactic space that potentially got stuck there for some unknown reasons, with the first explanation that the scientists provided basically being dark matter. There is a possibility that some of these stars essentially got trapped by various dark matter clumps, preventing them from re-entering various galaxies. Now this is just a preliminary explanation and obviously there's no evidence for any of this, but it was still an intriguing discovery. Right now it's still unclear where a lot of this extra light is sort of coming from. The next image is this, a spiral galaxy, specifically a galaxy known as IC 342, also sometimes known as the Hidden Galaxy, mostly because of its location behind the galactic equator of the Milky Way, so basically it's a little bit difficult to see it. And though we did actually have some really good pictures of this galaxy before, it looks like now we have an even better image. Way more detailed, presenting a lot more hidden objects, and most importantly, all of this was just captured in 1 hour. By looking at this location for a single hour, Euclid was able to produce this. And that is just mind-blowing, making this the first ever space telescope that's able to capture an entire galaxy so quickly and produce such incredible results. And though there are not a lot of discoveries coming from this just yet, there are definitely a lot of mysteries. This galaxy is about 11 million light years away from us, and as you can see this is a large spiral galaxy, but unlike other spiral galaxies, it surprisingly does not have a lot of satellites. And so the mystery of this galaxy and how it evolved, and why it seems to be predominantly alone with just one single satellite known to us, is one of the questions the scientists are going to try to answer. But it also took a picture of a much less developed galaxy, taking a very beautiful picture of an irregular galaxy known as NGC 6822. Here's how this image compares to the previous one from the extremely powerful La Silla Observatory in Chile. And so this galaxy that's about 1.5 million light years away from us is very similar to Small Magellanic Cloud both in size and in composition, essentially representing a kind of a primordial galaxy with a lot of material that we normally find in early universe and not a lot of star formation either. And this super accurate image shows us features we've never seen before. I'm sure it's going to be explained later on when the studies come out, but even from previous observations, we know that there are some signs of star formation, and specifically ancient star formation, that seems to have happened about 4 billion years ago. And intriguingly, some of the observations from its motion in the night skies suggest that it might have actually passed not so far away from the Milky Way at this time, implying that maybe, just maybe, it's actually the Milky Way that suddenly caused a star formation burst inside this galaxy. Now, because it's only 1.6 million light years away from us, it's definitely possible. And so trying to figure out if there was any mixture of material, or if maybe some stars were exchanged in the process, is of course going to be super exciting for some of the future studies. At the moment though, we just get this ridiculously beautiful, very detailed image. And then we also got two images much closer to home. The first one is of an object about 8,000 light years away, and this is a collection of hundreds of thousands of different stars. This is the second closest globular cluster. Here's actually a comparison of the same image taken by the Hubble. So just look at the difference. Absolutely insane. And what makes this cluster a little bit unusual is first of all that it's kind of compact, but second of all is that it seems to have a lot of mass right in the center. And at first it was believed to be maybe black holes, possibly even a large black hole. But then the simulations and a lot of observations reveal that it's very likely hundreds and possibly even thousands of very compact white dwarfs, all kind of bundled right in the middle, making this one of the stranger clusters out there, but something we expect from an object so ancient. It's about 13.6 billion years old, very likely one of the first globular clusters to appear in the Milky Way. And now we have this new beautiful image that beats the image from Hubble by a mile. Not to mention that once again all of this took almost no time, and in this case the entire cluster was once again observed as the entire object, producing the most accurate observation ever. But once again revealing maybe one surprise. It looks like for some reason this cluster does not seem to have a lot of trailing stars. All of the stars are kind of concentrated around the center and all seem to move as basically one object. And to dark matter scientists, this once again suggests that maybe there is some kind of a dark matter mystery involved here as well. It's not clear what's happening here just yet, but something is definitely happening. And the last image was the one closest to planet Earth, the famous Horsehead Nebula, approximately 1400 light years away from us. This is of course inside the Orion Nebula. Here's how this compares to the image from Hubble. And here we basically have dark clouds in front of very bright ultraviolet radiation coming from Sigma Orionis, one of the stars nearby. And though by itself this telescope is not actually meant to study nebula, and the James Webb Space Telescope is definitely much better for that, even here it was able to impress. All of this once again just took 1 hour, and all of this uncovered a lot of objects we've possibly never seen before. Scientists are actually hoping that there are quite a lot of Jupiter-sized planets here, or maybe a lot of baby stars we've never seen before, but at the moment we don't really know which ones are new and which ones have been studied before. I'm sure the studies in the next few weeks will tell us more. And so honestly, all in all, when you look at these pictures, comparing them to the originals, it becomes pretty clear that this is an incredible machine. And just like the James Webb, it's going to be revealing the universe in a way we've never seen it before, by essentially providing these super sharp images with thousands and millions of new objects we've never seen before, and more importantly, creating the biggest three-dimensional map of the universe we've ever had, but also eventually helping us figure out what exactly is happening with dark matter, dark energy, and most likely solve other mysteries as well, and all of this within the next 6 years. Because at the moment, that's essentially the mission plan for this telescope. In the next 6 years, it's going to collect enough data to create the largest map. And I guess after seeing these images, I actually cannot wait. As a matter of fact, I can't wait to see even more images, because this so far was definitely better than I expected. Way better. Hello wonderful person, this is Anton, and let's discuss dark matter once again.
a phenomenon that we still don't really understand very well, but that we're almost certain exists, based on the observations from various galaxies, measurements from various galactic clusters, and observations and measurements from gravitational lensing effects, all of which would be impossible to explain unless there was something else, somewhat invisible, creating all of this extra mass. Something that could be up to 85% of all of the matter in the entire universe, and something that seems to be responsible for the majority of a gravitational pull in the entire universe. But what exactly it is, or more specifically, what it's actually made out of, is of course that one big mystery of the entire universe. After years and years of search, nothing has so far been discovered definitively. But there's actually a really big playlist about this in the description below that goes through some of the ideas and some of the propositions. The most likely explanation right now involves what's known as axions. But in this video, we're not really talking about dark matter as a phenomenon or potential explanation of dark matter. We're talking about an extremely unusual, unexpected, and very difficult to explain observation from a pretty well-known galaxy. Here's the actual image. This is NGC 1277, an extremely old galaxy that's actually even referred to as the relic galaxy, that's most likely at least 12 billion years old and was originally discovered back in 1875 by Lawrence Parsons. And the reason it's called the relic galaxy is because of previous observations with various telescopes that established that this unusual galaxy most likely did not interact with a lot of neighboring galaxies, remaining untouched for billions of years. And so unlike a lot of other galaxies, including the Milky Way, that often have a lot of collisions, this particular galaxy might have remained completely untouched for a very long time. And so this unusual lenticular galaxy, located 240 million light-years away from planet Earth, that's even several times more massive than the Milky Way, has always represented an intriguing target for studying galactic evolution and for learning about mysteries of the entire universe. But a lot of modern theories and a lot of models generally predict the existence of dark matter as the biggest part of mass in pretty much all galaxies in the entire universe. As a matter of fact, it's expected that a galaxy of this type would most likely have approximately 70% of mass as dark matter. And that's because of the modern theories explaining the formation of early galaxies. It all usually starts with the invisible cosmic web that seems to propagate the entire universe. This is most likely the foundation of all galaxies and predominantly is made out of dark matter. For example, because many of these galaxies are formed along the cosmic web, it was previously used as an explanation for why so many different galaxies relatively far away seem to contain relatively similar orientation and even rotate in the same direction. So basically this cosmic web, or dark matter-based cosmic web, seems to be responsible for everything. It's sort of like the skeleton of the entire universe. Here's another way of trying to visualize this. And so inside this cosmic web, a lot of dark matter particles form what we refer to as halos that then attract a lot of hydrogen, making it swirl in the middle and eventually forming larger structures that eventually become galaxies. And as all of this gas is pulled into much denser clouds, it eventually results in star formation and physically visible galaxies. Or that's of course the best explanation we have right now for what we're observing from various galaxies and why so many stars in these galaxies seem to be rotating or orbiting around the center much faster than they should be orbiting. But that's of course not the only explanation. There's another explanation known as MOND, or Modified Newtonian Dynamics, that essentially tries to rewrite the gravitational formula and is able to explain some of the observations we're observing from various galaxies. Or basically, by rewriting Newtonian formula, it's able to achieve somewhat similar results. And so quite a few scientists have accepted this idea because it doesn't actually require any dark matter and seems to explain at least some of the observations. And actually there are some other explanations as well, but MOND right now is probably the most popular alternative to dark matter that does not require too many modifications. Just a quick side note, in the past we've discussed a few discoveries that basically violate everything proposed by MOND and make it essentially wrong. You can find some of these videos in that playlist in the description. But one of the main points of MOND is that, assuming that it's correct, we're going to be observing very similar patterns in various galaxies, with essentially all of them appearing to contain dark matter
and stars appearing to move really fast. And if there are no actual exceptions to this rule, there is actually a chance that maybe Mond is correct and maybe dark matter as a particle does not exist. Maybe it is all just about rewriting some formula. Once again, side note, it's not, but let's just keep going with this. And so here we then have two major explanations. Either dark matter is some kind of an invisible particle that we still don't understand and are having trouble finding, basically responsible for most of the mass in the entire universe, or the formula for Newtonian physics was always incomplete, and by rewriting it, everything suddenly makes sense. Both of these explanations would then be able to explain why galaxies spin in such an unusual way, but only one of these explanations would be enough to explain everything else, including unusual gravitational lensing and extremely large galactic clusters that would not make sense otherwise. In this case, the explanation required for all of this is an invisible particle and not a rewritten formula. But I guess more importantly, to some extent there is a way to invalidate one of these ideas once and for all, by discovering something that's completely unexplainable in one of these propositions, such as for example a really unusual galaxy that just doesn't obey any of the propositions involving dark matter or rewritten formula. And well, here we go. Here's that one galaxy. A giant, really massive galaxy, several times bigger and more massive than the Milky Way, that for some reason seems to show no signs of dark matter, challenging everything we understand and everything we know. A galaxy that was recently reanalyzed by the scientists from Instituto Astrofísica de Canarias that analyzed the property we usually refer to as the galactic curves. In a typical galaxy like the Milky Way that has a lot of dark matter, we actually expect all stars to orbit at a relatively similar velocity, no matter how far away they are from the center. Not so for galaxies that seem to lack dark matter that we've discovered previously, that seem to actually have something very different. Here, the stars that are much farther away orbit much slower as well. We've discussed these galaxies previously, but all of the previous discoveries were usually extremely small, very low in mass, and even barely visible. These were usually what's known as UDF or ultra-diffuse galaxies. This is the first one discovered so far that's basically extremely similar to the Milky Way. And so by observing this galaxy for a pretty long time and trying to understand what's going on here, the current suggestion is that it might only contain about 5% of dark matter by mass, out of expected 70% at least, with the results from this paper working out extremely accurate details up to about 20,000 light-years away from the center of the galaxy. And so at least in the center of this galaxy, the current observation suggests extremely low presence of dark matter. Now for ideas involving invisible particle, there are some potential explanations that we're going to discuss shortly. But for ideas like Mond, that's the end of the story. There's no way they can explain this, and it basically invalidates everything here because you cannot rewrite gravitational formula and get the same results. So yeah, once again, this is most likely completely incorrect. But we might have some explanations for what happened to dark matter after all. Well, the first, this galaxy is actually not really that usual. It's not a typical galaxy. Despite having almost no interaction with anything, for some reason it does contain a really massive black hole in the center. As a matter of fact, some of the initial estimates suggested that this was one of the most massive ever found. It was believed to be about 17 billion solar masses. Eventually this was recalculated, and today we believe it's maybe about 1 to 2 billion solar masses. Still much larger than anything in the Milky Way, 250 times more massive as a matter of fact. On top of this, a lot of stars in this galaxy very likely formed in the first billion years of the existence of the universe. It really looks like most of the stars formed in just 100 million years, around 12 billion years ago, and stayed here completely unchanged ever since. Which is one of the main reasons we refer to this as the relic galaxy. It's a relic of the early universe, the universe that was forming stars in the first couple of billion years. And surprisingly, the stars here were formed really fast, very likely 1,000 times faster than the current star formation in the Milky Way. So basically here, all of the stars appeared very suddenly, all at once, and have not changed much since. And because this galaxy stayed isolated without any collisions, and the black hole was pretty much quiet this whole time, yet managed to achieve extremely high mass, the implication here is that at some point it's quite possible the black hole shut down the entire star formation in this whole galaxy. So basically the black hole stopped stars from forming ever again. And so all of the stars here are really old, at least 7 billion years older than our own Sun. And strangely enough, or even more surprisingly, this galaxy does not contain any metal-poor globular clusters that are usually very common in other galaxies, which confirms that it's a relic galaxy that did not get a chance to interact with anything else and did not accrete mass from outside of the galaxy. And so the globular clusters, which often come from other galaxies, never really arrived here either. But the fact that it also has very little dark matter, that's the mystery that we currently cannot explain. Okay, there are some propositions, but nothing concrete and nothing certain just yet. The first one is kind of obvious. Maybe because of its position along the cosmic web, some of the medium surrounding this galaxy essentially stripped it of all of the dark matter over time. It's not clear how it did so, but because this acts kind of like a stream, it's possible that it just kind of left the galaxy with nothing stopping it, especially if there was more mass surrounding the galaxy compared to the galaxy itself. Now this is not something that's going to be easy to prove, but that's one potential explanation, especially because it has been used before to explain other similar galaxies containing extremely low amount of dark matter. And the other explanation involves the initial formation of this galaxy. Maybe during the initial formation, as the galaxy was formed from initial gas, because of the gravitational interactions, quite a lot of dark matter was basically driven away due to various gravitational interactions with all of the other stuff that was responsible for the formation of this galaxy. Now that's also something that's going to be very difficult to prove, but it could be proven using computer simulations. But physical evidence would not be very easy to discover. Nevertheless, this is a really important discovery. NGC 1277 is one of the most important galaxies identified in the last few years. But obviously none of these answers or none of these observations are certain yet. For example, to confirm this, the next step is going to involve William Herschel telescope. It has an instrument known as JWST Enhanced Area Velocity Explorer that's going to be able to definitively determine if the actual results here, or the observations from this galaxy, are indeed as anomalous as they were presented in this paper. And following this, we have the ESA's Euclid telescope and the NASA's Nancy Grace Roman telescope, both of which are planned for the next few years, that are hopefully going to provide more results and more explanations. So as you probably know by now, one of the bigger mysteries in the universe is the mystery of dark matter, with the mystery of course being exactly what it is. Is it some kind of a particle? Is it some kind of a phenomenon we don't understand? Is it some kind of a formula we have to rewrite? What exactly is it? And why does it produce so many effects around the universe? Because basically that's how we know dark matter is real. It produces so many unusual observational effects that cannot be explained otherwise. And one of the most common explanations today involves some kind of a mysterious particle that the scientists are trying to discover that potentially produces all of these extra gravitational effects. And if you want to find out why the scientists believe dark matter is real, check out one of the previous videos somewhere in the description. But today we're actually going to be focusing on something else. We're going to be focusing on the exciting research of the search for dark matter. Because basically a lot of modern technologies are usually created through various unusual searches in various scientific fields where the scientists try to find something and then realize that all of these inventions they've just created can actually be used for a lot of other fields as well. Which is actually why dark matter research is so important. It's definitely going to lead to a lot of exciting technologies. And so the purpose of this video is to explore some of the upcoming research in search for dark matter, or to basically take a look at some of the new techniques the scientists propose that we can actually use to look for these unusual phenomena or these unusual particles, in the process helping us develop technologies even more. And let's actually start with one of the more unusual ways I've discovered so far. At least one scientific paper proposes that we can actually use DNA to detect dark matter, or to potentially detect something else entirely, some other effect, that can actually lead to some major breakthroughs. And so here's what the scientists actually proposed a few months ago. This is from a paper you can find in the description below. They proposed creating a miniature detector by suspending very long DNA strands as you see in this image. In this case, the actual DNA doesn't matter, it just has to be really long and has to be suspended in a very similar way to much larger strands in a neutrino detector such as IceCube located in Antarctica. So the principle here would be very similar, but in this case, by suspending the DNA from a gold metal sheet and by putting the strands in a very specific location, but also creating each DNA strand with a unique identification system, it becomes possible to track any kind of a disturbance within this detector when a particle passes through this and disturbs it, dislodging some of the strands. And so by slicing through some of these DNA strands, it will then deposit certain strands on the bottom, with these strands then amplified using various PCR techniques in order to determine which strands were affected. And because the strands would be very specific, it actually allows the scientists to then even create a kind of a 3D map showing a precise location where this particle very likely came from. Although naturally, this DNA would also be affected by a lot of other things. Cosmic rays, all sorts of radioactive decay, even neutrinos, will most likely damage the DNA and result in some kind of a detection. And so in this case, by actually doing this for an entire year, it becomes possible to determine if certain detections are, for example, due to the rotation of planet Earth around the Sun. And some of the previous papers have even suggested that in March we should expect a little bit more of dark matter particles because of how Earth and the Sun move around the galaxy. And so if the scientists do detect more detections during those periods of time, it might suggest that this detector is definitely working. Although in this case, the assumption is that there is going to be at least some effect when a dark matter particle passes through the DNA itself, which already has another implication, of course. If dark matter is real, it might have also influenced the evolution on our planet by basically helping DNA evolve. But that's a little bit beyond the scope of this video, and we'll discuss this in some of the future videos on this topic. Nevertheless, even if not dark matter, this is a pretty cool detector for a lot of other reasons. First of all, it would be extremely cheap to produce, it would also be really small, it would also be very power efficient, and more importantly, it could be used to detect a lot of stuff on a planet, including a lot of other mysterious particles that the scientists have been trying to discover for a very long time. So definitely a cool proposition. By the way, just as a side note, one of the most famous experiments today is the one behind me. It's known as Xenon. And it's actually one of the experiments that potentially detected something unusual a few years ago. The scientists are still not entirely sure what it found, but it's one of the reasons they actually keep going with the experiment and keep trying to rediscover whatever it is they found originally. But the video in the description explains this in a little bit more detail. Anyway, moving on to the next proposition. Atomic clocks. And specifically, a spacecraft-based atomic clocks that actually already exist out there because a lot of satellites use atomic clocks today, that the scientists think we can use to try to discover what happens very close to our Sun, specifically in the region between Mercury and the Sun itself. Now this region, if dark matter exists, and of course if it's some kind of a particle, would represent the location with the highest possible density of dark matter present in the solar system, mostly because most of it is probably going to approach closer to the Sun and is probably going to be trapped in orbit much closer to the Sun as well. And so the region between Mercury and the Sun is very likely where we're going to be finding more of these particles, if they exist. And so by placing an atomic clock on a satellite and putting it in orbit very close to the Sun, we might start observing discrepancies or oscillations in the measurement of time using this atomic clock. And the idea here is really simple. If dark matter particles exist, just like a lot of other mass in the universe, as they pass close to certain objects, they're going to induce certain gravitational effects, or potentially even induce certain effects on the various constants of nature, such as the iconic fine structure constant, which could affect the electromagnetic forces, and thus affect the measurements in the atomic clock as well. And that's because the atomic clock measures the frequency of photons emitted when atoms transition from one state to another. And so a certain type of a dark matter particle can actually change these effects, making these observations possible in certain locations of the solar system, such as close to the Sun or close to Mercury. But this type of mission does not have to be designed specifically to find dark matter. As a matter of fact, a lot of modern spaceships at some point will require atomic clocks for their own internal purposes, such as to measure time, to then determine distances and location in space. And so just by virtue of exploring the solar system in some of the future spacecrafts, we might actually be able to collect enough data to potentially discover something interesting somewhere in the solar system by looking at the discrepancies in the atomic clocks present in those spaceships. And by figuring out how to miniaturize these and make them much easier to transport, we might actually come closer to having these spacecrafts much sooner than we would have them otherwise. Okay, 2 down, a few more to go. Next one is also kind of intriguing. It actually uses technology that we use for something else. meteor detectors, specifically detecting various asteroids or various meteorites that enter the atmosphere of our planet, producing quite a lot of plasma, which leaves behind a very interesting electromagnetic effect known as the ionization trail. And so this is how a lot of meteoroids that enter our planet are usually tracked from various sources, which is exactly how the scientists then determine where they crashed, by basically tracing the tail. But at least in theory, certain types of dark matter can also leave behind these ionization trails, but obviously without the actual collision, without the actual rock. Although in this case, this would be dark matter that would be much more massive. A particle or even a chunk with a large mass equivalent to a typical rock. And so by using a very similar technique, and by looking for these ionic tails that are formed without an actual meteor, it might become possible to find certain anomalies that could not be explained otherwise. This would resemble a sudden influx of a lot of electromagnetic waves released by the radar as it bounces from all of these free electrons, suggesting that something else is going on here, and potentially implying that we found a very chunky dark matter particle. And since in this case the entire planet can be used as a very large particle detector without any use of new technologies, at this point it really becomes just a matter of data processing and data collection. Something that in theory the scientists can even do today. They haven't yet, but it's definitely possible. So definitely a pretty cool proposition. Another proposition looks like this. By trapping an electron, it actually becomes possible to use it to track any kind of a particle that passes through the region of space where the electron is located. And in this case, by using a laser, it becomes even possible to detect the exact mass of this particle and to determine a lot of other properties. Although here, like in a lot of other cases, it's assumed that there is some kind of interaction between electromagnetic forces and dark matter, or that the dark matter particle is at least a little bit charged. Nevertheless, if not dark matter, it can also be used to detect something else. This hasn't been built yet, it's just a theory, but it's a pretty cool proposition. Trapping one electron in a very highly controlled environment can definitely allow the scientists to find something unique, invisible to us otherwise. And then the last proposition is from the paper you can find in the description. A slightly more complex proposition, using superconducting nanowire detector. In this case, by using a tungsten silicide superconducting nanowire, super thin, only a few microns or even a few nanometers in thickness, can actually create what's known as a superconducting nanowire single photon detector, a technology that existed for approximately a couple of decades now. And these devices are extremely sensitive to very small amounts of energy, usually being able to detect even a single photon. Here is one of these devices from approximately 15 years ago. And the way that this works is really simple. The scientists take these superconducting wires that are super thin and cool them down just above their limit. Or essentially they turn them into a superconductor, but just a little bit different from that superconducting temperature. If you warm it up just a little bit, it will suddenly lose its superconductivity and acquire electrical resistance. And so in this case, even a single photon of a certain energy will affect this and will switch off superconductivity, which can then be detected by measuring the electrical resistance and seeing the differences. And these devices are already actively used in various quantum computers because they're so accurate at detecting even a single photon of light. But by building an array of these, it becomes possible to actually keep track of an entire area where these particles could pass through, affecting the superconducting wires underneath. These nanowires, when fabricated, would look something like this. Really small, but extremely accurate and extremely precise. And so in this case, the scientists were able to even fabricate a prototype of this particular device and even give it its first test run. Although in this case, they were looking for another type of a dark matter particle, the hypothetical dark photon, which in theory could be found by these detectors relatively easily. But according to the scientists in this paper, having run this experiment for 180 hours, so far they found no evidence of these dark photons existing. Although in this case they were only looking at a very specific mass. By scaling up this experiment and making it larger and longer, it might lead to some discoveries in the future. But I guess more importantly, it might lead to new technologies used in a lot of different industries, specifically quantum industries. And so scaling this in size might eventually lead to even better quantum computers. Or it might in theory. At the moment, nobody really knows where any of this leads, or if any of these are even going to be developed. And for all we know, maybe dark matter is not really a particle. With all of this potentially remaining as a kind of a theory, as a kind of a suggestion, and nothing else. But these are still really cool propositions, and some of them are actually really intriguing, so maybe some of the scientists might be able to try this in the future. If not to find dark matter, maybe to discover something else we do not see otherwise. Hello wonderful person, this is Anton, and today we're going to be discussing a relatively new proposition and a relatively new study that finds unusual evidence that black holes may be directly connected to the idea of dark energy. And more specifically, they seem to actually maybe even produce it to some extent. Although in this case, it's also important to understand that all of the discoveries in this paper so far are really more or less correlational, not causational, indicating a direct relationship between dark energy and black holes, but not necessarily showing that one causes the other, although there have been theories proposing that as well. So let's discuss this in a little bit more detail, but because this is such a loaded topic, I do have to make a few clarifications about what exactly is going on here, and what exactly we currently believe about dark energy, dark matter, and so on. As you might have learned from some of the previous videos, some of which you can find in the description below, today the scientists believe that inside our universe, we don't just have visible matter, so things like atoms and things that we're made out of, but we also seem to have certain mysterious invisible things that we only are able to see because of their effects on matter around them. So for example, the invisible dark matter that's responsible for creating a lot of gravitational effects that would be almost impossible to explain otherwise. A good recent example here is from the James Webb Space Telescope that shows us this very famous galactic cluster where gravitational lensing effects from something invisible in the center allow the scientists in the process to discover a lot of really exciting things. Very distant galaxies, very distant stars, and a lot of unexplained phenomena in the process. You can obviously learn about this in some of the previous videos about James Webb Space Telescope. But these gravitational effects cannot be purely explained by actual visible matter such as gas and stars. Something else is going on here. And so today the scientists believe that approximately 27% of everything in the universe is this invisible dark matter. But in 1998, so basically over 2 decades ago, a lot of older images from the Hubble telescope revealed something else very unusual. They helped the scientists discover that distant supernovae were for some reason actually recessing away from us much faster than they should be. Or in other words, that the universe was expanding faster and faster as you move away in time. And this unusual discovery led to major propositions about the universe. It looks like the universe was not just expanding, it was also accelerating its expansion. This was the so-called dark energy, the mysterious something that's causing the universe to expand faster and faster and faster. And it seems that there's actually a lot of it. About 68 or maybe even 70% of everything in the visible universe. This proposition, by the way, resulted in a Nobel Prize a few years later. But the important part here is of course that, well, this was the original discovery of this unusual phenomenon that we actually still have no idea how to explain. Some scientists or some physicists suggest that this is basically a constant, part of a formula where things just expand because it's, well, in a formula. The formula, originally proposed by Einstein, known as the Einstein field equation, with the cosmological constant presented as lambda, directly connected to other constants such as the Hubble constant. But this is exactly where the problem starts. After years and years of measuring and investigating things with several different telescopes, the scientists started to discover that, well, it doesn't actually seem to be that constant after all. It might have actually changed in time. Today this is known as the Hubble tension, and it's essentially a series of various observations that all seem to imply that there might be 2 different values of this unusual constant, depending on where exactly you look at. But that's just one of the problems. The other problem is that the actual formula does not provide the explanation for what exactly is creating these effects. If this is just a constant, just a number, it still has to have some kind of a physical explanation. And so this physical explanation currently is just known as the dark energy, sometimes explained with the unusual phenomenon known as the vacuum energy. The phenomenon that exists because of quantum physics, and a phenomenon that has been to some extent shown to exist from various other observations based on a lot of smaller experiments. It basically suggests that there is no such thing as vacuum. Empty space does not exist. Even inside empty space, you're always going to have these minute fluctuations of energy that are going to always end up creating various particles that appear and disappear because of quantum fluctuations. And since, according to Einstein, energy and mass are equivalent, and both also result in gravitational effects, we should observe some effects because of this vacuum energy observable throughout the entire universe. This is also sometimes referred to as the quantum vacuum state, and there have been quite a lot of different experiments directly showing us that the vacuum fluctuations definitely seem to be a real phenomenon that seem to exist. And the first such experiment was actually conducted back in 1948. This is the experiment of Casimir effect that we've discussed in one of the previous videos. Something that technically you can even perform yourself if you have a sensitive enough apparatus to measure pressure. In a nutshell, the experiment shows that empty space between relatively thin plates will actually start receiving a lot more pressure from the outside because the space on the inside is small enough that not enough quantum particles are going to be produced, which results in actual physical pressure, even though all of this is vacuum and there's really nothing on the inside. This experiment is pretty well known and a lot of scientists try to maybe explain it in other ways, but at the moment the quantum fluctuations is really the best explanation and provides direct evidence for this vacuum energy. But, like always, the original explanations were from someone else. Probably one of my most favorite people in physics, Georges Lemaitre. He explained all of this in 1934. He basically tried to interpret the cosmological constant by combining it with perfect fluid equations of state and by physically showing that it could be some kind of an energy or even some kind of a particle. And as you might have learned from one of the previous videos in the description, completely by accident, a Belgian TV station discovered an interview with this absolutely brilliant person who even today is still sort of underappreciated. I mean, we're talking about a person that was able to prove Einstein wrong, and that was also the first to propose a lot of these brilliant ideas. But that's beside the point. Check out the video in the description if you want to learn more about him. The main point here is that the more the scientists tried to understand dark energy, the more confusing it got. But it seemed to be an actual phenomenon, causing the universe to expand faster and faster. And more importantly, it seemed to be directly connected to the fabric of the universe itself, but its actual source was still not entirely understood. But a few years ago, we've discussed another intriguing study that actually discovered something unusual about supermassive black holes in very distant galaxies. They discovered that if you were to look farther and farther away into the universe itself, a lot of black holes, on average, seem to be a little bit more massive than they should be, as if there was some kind of a connection between black hole mass and the expansion of the universe itself. And though it was an intriguing proposition, not a lot was done with it back then, and not a lot was actually explained from this observation. Now, however, in a new study, the scientists found even more evidence that a lot of central black holes in very distant galaxies seem to be directly connected to dark energy, or even could be the source of dark energy. Or to be more exact, discovering first evidence, for what's known as cosmological coupling between dark energy and black holes across the universe. And this concept of cosmological coupling just simply relates to how the universe evolves over time and how things like temperature, density, structure, and a lot of other parameters inside the universe change as the universe grows larger and larger. With one famous example being the cosmic web, the structure inside the universe that directly evolved over time as a result of the expansion of the universe and as a result of dark energy very likely pushing on the web itself and making it stretch over time. But in this case, the scientists have also discovered that this cosmological coupling applies to the masses of very massive black holes, but also in galaxies where the black holes should not be growing at all. And specifically, we're talking about galaxies like what you see right here, the elliptical galaxies. Galaxies that predominantly have a lot of really ancient stars, but practically no activity anywhere. No star formation, no galactic collision, with the black hole at the center maybe being a little bit active, but not absorbing a lot of mass and definitely not growing very fast either. And more specifically for their study, they focused on the very inactive elliptical galaxies from various regions in the universe, anywhere from being extremely close to us up to several billion light years away. Or in more cosmological terms, anywhere from the redshift of 0 to the redshift of 2.5, which in this case suggested that these black holes should not be accumulating matter and growing from normal processes understood by previous studies. If they were growing, it was for an entirely different reason. But when comparing the masses of these black holes inside these galaxies to the predicted value, they discovered that as the universe progressed in time, the black holes increased in mass as well, with a confidence value of approximately 99.98%. Still not perfect, but definitely something intriguing that needs to be investigated even more. And on top of this, by removing the mathematical concept of singularity and replacing it with vacuum energy, or essentially making these black holes as vacuum energy black holes, this allowed them to directly explain the expansion of the universe as observed by various telescopes. First of all, suggesting that black holes are definitely not just empty points with an infinite point on the inside, the concept referred to as singularity. Instead, they seem to be much more complex, potentially even being the source of huge amounts of vacuum energy, most likely through some kind of a quantum interaction that we still don't understand. Or essentially, they don't just produce extremely powerful gravitational effects, but on top of this, they seem to produce huge amounts of vacuum energy, which potentially causes the universe to expand even more. Which once again means that we just don't really understand black holes very well yet, and there's still a lot to explore. But naturally, because this is such a huge proposition, it will probably take months, if not years, to confirm or disprove all of this, and a lot more observations and a lot more analysis are required as well. More importantly, because they've only used less than 10 galaxies to measure this would first have to be confirmed by looking at hundreds, if not thousands, of different galaxies to see if the same effects apply there as well. Hello wonderful person, this is Anton, and in this video we're going to be discussing an intriguing new paper that tries to tackle the mystery of dark matter. But it does so in a very unique way. It actually compares the idea of dark matter to a very peculiar state of matter that we know exists here on Earth and we can actually produce in a typical lab environment. This right here is known as BAC, Bose-Einstein condensate, sometimes also referred to as the fifth state of matter, because unlike solids, liquids, gas, or plasma, BACs can also exist for a very long time in certain conditions. Pretty much any matter can become this, but it also contains a lot of properties that other states of matter do not possess. And so in this video I wanted to explore this idea a little bit more, because what the scientists have recently identified by using simulations and relatively complex math analysis potentially provides a very interesting explanation to the mystery of what exactly is dark matter. The mystery of expecting to see a lot of invisible matter out there based on various effects and based on a lot of gravitational lensing from various distant galactic clusters, as well as effects from various galaxies where the stars are moving way faster than they should be moving based on all of the observable matter and all of the gas. And so, as you might have seen from previous videos, which by the way should be in the description, in the past there have been quite a lot of different explanations for what exactly is dark matter. And not so long ago, one of the recent papers was able to sort of definitively show that dark matter is unlikely to be some kind of a very large, very massive particle. The concept scientists refer to as WIMPs, weak interacting massive particles. And the recent studies suggest that it's unlikely to be that, but it can still be at least two other things. An intriguing other particle known as axion that is actually meant to explain something entirely different in physics, with the explanations about this somewhere in the description, or potentially a bunch of particles that are just extremely low in mass, or low in energy, and are thus just extremely difficult to detect. And it's that last explanation of these very small, very low in mass particles that the scientists wanted to focus on. Specifically, they actually wanted to simulate what would happen if you had very low in energy particles, more or less interacting across large volumes of space. And so by using relatively complex simulations, they were able to create something that's thousands of light years in length, to some extent representing a center of a typical galaxy. But intriguingly, what they discovered is that these particles will actually start exhibiting quite a lot of effects similar to a typical quantum system. In other words, because of their low mass, they start having what's known as wave interference, which start producing a lot of turbulent effects, including various vortices, and a lot of fluctuations that are a little bit different from what we expect from a typical gravitational system. But more importantly, it reminded the scientists of something that we actually can make right here in a typical lab on Earth, and something that's entirely quantum in nature. And so here I wanted to briefly explain what exactly a BAC is. Originally described and predicted by Einstein and an Indian physicist, Satyendra Bose. And in a nutshell, it explains how certain particles, which we usually refer to as bosons, in certain extremely cold conditions and also in relatively low densities, will start increasing their interference waves until those waves start interacting so much that they actually turn into one massive wave that starts to acquire not microscopic but macroscopic properties. It basically becomes a single collective quantum wave. And it's this unusual quantum wave that can easily contain hundreds, thousands, or even millions of different particles that then starts to exhibit these quantum effects that become visible on a much larger scale. In other words, the actual particles disappear and they become basically a large massive wave. Okay, honestly, it's kind of difficult to imagine exactly what this becomes, but here's how it's visualized by NASA. And here's how it's visualized by the National Institute of Standards and Technology. And a lot of modern studies in quantum physics usually rely on Bose-Einstein condensates to try to figure out exactly how quantum effects work and what happens in certain conditions. More intriguingly, in one of the recent studies, and I think this was like a study from a couple of days ago, the scientists were definitively able to show that the famous EPR experiment that basically proved the non-locality of the universe definitely seems to work for backs as well. Or in other words, you can actually affect one back, quantum entangled to another back, and both of them will have entanglement effects no matter how far away they are, even if you place one of them hundreds of light years away from planet Earth. Now we're actually going to be exploring this idea a little bit more in one of the future videos, so do subscribe if you want to learn more. But in a nutshell, this is a proof that even really large objects, containing hundreds, thousands, and millions of atoms, once entangled and once they achieve a quantum state, will actually possess all of the quantum properties we expect. But we'll talk more about this in some of the future videos. For now, let's focus on backs and how it connects to dark matter. So basically, backs are a state of matter that's assumed when a bunch of particles, in this case bosons, sort of connect their interference wave, basically combine into one large massive particle, or technically a large massive wave. That of course relates to the idea of particle-wave duality. And so when the scientists were conducting these experiments with hypothetical dark matter of extremely low mass and low energy, they actually realized that it seems to possess extremely similar properties to a typical back. And so even though we generally associate dark matter with something related to gravity, which basically forms the cornerstone of entire cosmology, this particular simulation and this experiment sort of directly connected this to ultra-cold atomic physics, describing behavior of cloud of atoms, specifically atoms like rubidium and potassium, as an unusually similar model to what we might observe with hypothetical dark matter particles, and more importantly connecting this to an idea that already exists. An idea in cosmology known as fuzzy cold dark matter, or the idea that involves these extremely low in mass particles potentially being responsible for all of the dark matter effects that we're observing from around the universe. And particles whose wavelengths would have to be extremely long, possibly a few light years in length, making them practically undetectable by modern techniques. But because they're present in very cold conditions, and because their wavelengths are already so long, at some point they would start interacting with one another and eventually form some kind of a very large collective, entirely quantum in nature, but also possessing a lot of effects that we still do not understand very well. And so basically by bringing two disciplines into this, the discipline of cosmology and ultra-cold atomic physics, the scientists actually found a really intriguing way to potentially solve this mystery. But I guess more importantly, presenting us with an opportunity to study this and to physically prove or disprove this by not looking out there somewhere in the universe, but instead recreating a model universe right here on Earth by using tiny galaxies made out of Bose-Einstein condensates. And here, even in their own simulation, they were already able to create something resembling a dark matter halo, or basically a gravitational structure that we usually believe is responsible for holding the galaxy together. But in their simulation, they also were able to observe unusual turbulent states and unusual vortices that existed outside of this halo, all of them a result of quantum effects, assuming that this is exactly what dark matter is, should be visible somewhere out there in the universe as well. And so here, the centers of these halos seem to actually possess extremely similar properties to gigantic Bose-Einstein condensates. And the farther away from the halo you move, the more wave-like behavior and the more unusual quantum properties should be visible around various galaxies. But here, even though the core itself seems to possess back-like properties, outside of the core the effects become a little bit less predictable. Or I guess in simpler terms, if this is correct, the intergalactic space would potentially have a lot of unusual quantum effects that we cannot explain. And it's really these unusual vortices that seem to form as a result of the halo that would actually potentially prove this idea if we can somehow discover them in the intergalactic space. Either way though, this model actually presents the entire universe and every single galaxy in that universe as something that's more wave-like in nature, as opposed to something that's being driven entirely by gravity and particle interaction as modern cosmology presents it. And so in some sense, this is actually a pretty intriguing explanation, and an explanation that once again shows us that in some sense the universe is just a little bit stranger than we ever thought. But whether any of this is true, and whether any of this makes sense, only future studies will tell. For now, the only facts we have are that backs are real and do possess unusual properties, and that there does seem to be some kind of an unusual effect that we refer to as dark matter. But whether these effects are connected and potentially can explain one another, or if it's completely unrelated, that's not something we can definitively answer just yet. Hello wonderful person, this is Anton, and today we're going to be discussing both black holes and dark matter, two exciting phenomena that many scientists believe will help us explain the universe even better. And although we are pretty sure black holes exist, and there are quite a lot of them out there, when it comes to the mysterious dark matter, the story is not as clear-cut. The only evidence we have for this unusual dark matter is really circumstantial, but there is a lot of it. And I mean like a lot. And most of it is impossible to explain using any other explanation other than it's some kind of a particle or some kind of a mass that interacts with everything gravitationally, but not through electromagnetic means, which is why it doesn't produce light and seems to be kind of invisible. And though obviously it may sound kind of strange, it's not unusual for particle physics. As a matter of fact, neutrinos were also believed to be very hypothetical, taking many years to finally be discovered and to finally be proven. And so in that sense, a lot of scientists do believe that dark matter does actually exist as some sort of a hypothetical particle, it just nobody really knows what particle and where to even start looking. But this recent study actually provides even more evidence for its existence as a particle and not some unusual phenomenon or some unusual formula that we don't understand. With all of this coming from this study that as always you can find in the description below, with the title pretty much telling us everything. Indirect evidence for dark matter density spikes around stellar mass black holes. Because in this case what the scientists did was take a look at a somewhat old hypothesis in regards to dark matter and in regards to their relationship to black holes. And specifically, the idea that black holes can sometimes, or possibly even a lot of times, swallow dark matter and basically increase in mass as well. Which obviously suggests that a lot of other massive objects would probably be doing something similar as well. But naturally this means that while the black hole is swallowing dark matter, some of this dark matter is going to be orbiting around it, with quite a lot of it potentially coming really close to the black hole's event horizon, or maybe even assuming orbits around the black hole, possibly even permanent orbits. In other words, we know that black holes have an accretion disk, but there's also quite a big chance that some black holes, or maybe even all black holes, possess another accretion disk pretty much made out of some kind of dark matter. And since dark matter is believed to represent approximately 85% of all mass in the universe, it would not be surprising if these particular disks, if they existed, would be pretty massive as well. But unlike a typical accretion disk that produces huge amounts of light and is visible from the edge of the universe, anything involving dark matter would be pretty much invisible and only detectable through gravitational effects. And so knowing all of this, the scientists wanted to find out if this is actually what's happening around two relatively known X-ray binaries. Essentially a black hole and a star in orbit around one another. And this is by the way how the first black hole ever was confirmed as well. That black hole is known as Cygnus X1, and there is an older video on the channel that goes through a little bit more detail, both about the discovery and about recent discoveries from this unusual system. But in this case they did not focus on this black hole, they chose to focus on two other black holes in the Milky Way. XTE J1118 plus 480, the system that's easily visible in the X-ray frequency, with this X-ray image taken back in 2001, with the potential mass of this black hole being about 6 to possibly 7 solar masses, and A0620-00, slightly smaller black hole at possibly 5 to 6 solar masses, with this image showing us what it looks like using infrared light taken by Sloan Digital Sky Survey. And because this is a binary system with a star and a black hole inside, the light curve in this case looks something like this. And that's because the star orbits around the black hole, in this case approximately 7.7 hours per orbit, which allows the scientists to calculate extremely precise orbital parameters in both of these relatively distant systems. And so by taking a lot of data from these two star systems, and by looking at these light curves, and by specifically focusing on the changes in the orbital period, the scientists in this paper were able to calculate the overall orbital decay for both of these star systems, or essentially by how much the star's orbit decreases with every orbit around the black hole. And so, for example, because of the gravitational waves from the black hole, generally any object orbiting the black hole is going to slowly come closer and closer to the object. And that's of course how black hole collisions work as well. In this case, by producing gravitational waves, black holes cause one another to drop in orbit and eventually collide. But when the scientists took a look at these two systems, and obviously considered all of the possible effects, they realized that the orbital change was actually a little bit more dramatic. Or basically that the star decay in this case was slowing down by about 1 millisecond per year more than it should. And modern theories, including Einsteinian theories, cannot really explain this. And so instead, the scientists in this paper try to come up with different models trying to explain what's happening. In this case, using computer simulations to come up with a model that would try to explain this using what's known as dark matter dynamical friction model. Or basically a model that would consider the presence of dark matter as a potential source for the actual slowdown. In other words, dark matter orbiting a black hole and gravitationally pulling at these stars might be the reason why these stars in this case were slowing down a little bit more than they should. And the simulations did reveal that the observed rates were almost directly matched with the predicted model, which actually is a pretty big deal. Now, the original prediction suggested that the orbital decay should be close to about 0.02 milliseconds per year, but the rate that was observed from these two systems was approximately 50 times higher. So this was definitely a very significant effect that could not be explained in any other way. But once dark matter was added into the computer models, it all suddenly made sense. The observations and the predicted calculations were almost exactly the same, which basically confirms that black holes most likely swallow a lot of dark matter, and some of it is probably stuck in orbit around the black hole, forming its own version of the accretion disk, and thus having a lot of effects on objects nearby, which sort of makes this a really exciting study. But because this is a pretty big claim, it will definitely require a lot of follow-up studies and a lot of additional observations. As a matter of fact, in this study, the scientists already mentioned that we know of 18 more similar systems, and specifically 18 more binary systems, with at least one black hole, where all of this can then be investigated in order to either confirm or disprove these particular observations. And so chances are that in the next few years, as more scientists investigate those other systems, we might have even more understanding of what's actually happening here, and either finally have even more proof for the existence of dark matter, or maybe discover some new phenomenon that nobody ever knew existed. And though in theory it's also possible to maybe detect some of this from various gravitational waves coming from black hole collisions, nothing has been found so far. And so this is definitely the first ever official hint on the existence of dark matter around stellar mass black holes. Hello wonderful person, this is Anton, and today we're going to be talking about some of the recent discoveries in regards to the more unusual galaxies that we kind of think might not possess any dark matter. The mysterious phenomenon we still don't really understand very well, but the phenomenon that seems to be out there. And to be more specific, we're talking about these very iconic galaxies which are kind of barely even visible here. This one is known as NGC 1052-DF2. That in the past few years created a lot of problems for a lot of different cosmologists. First of all, compared to a lot of other galaxies of the same type, the diffuse galaxies DF2 and DF4 seem to possess pretty much nothing on the inside, only a few stars and only some gas, no dark matter whatsoever. Which creates a few problems for the scientists, but I guess the biggest problem is that nobody can explain how this happened. But more importantly, it invalidates various alternative explanations in regards to the idea of dark matter. But now we have this very new study that seems to go even further and discovers something else really intriguing. So let's talk about these discoveries, what all of this means, and more importantly, where we're most likely headed in the future. But let's start with a very important side note. At the moment, nobody knows what dark matter is. Nobody knows if it's actual matter, nobody knows if it's just a phenomenon or some kind of a misinterpretation in our observations. And up until this point, there was no good explanation for how certain galaxies seem to possess none of it. But there is dark matter phenomenon nevertheless. It's been observed from a lot of different things around the universe. From motion of the stars around galaxies, to various dilation effects that cannot be explained otherwise, to a lot of other unusual mass observations which can really only be explained as some invisible matter hiding between various galactic clusters. In other words, it seems to be there, but maybe it's not. Maybe it is due to our misunderstanding of how gravity formula work. For example, MOND, or Modified Newtonian Dynamics, tries to explain all of this by slightly changing the Newtonian gravity formula. And it seems to apply to some objects, for example, some motion of stars and different other objects in different galaxies, but the existence of galaxies with no dark matter creates a huge problem for this particular idea. Galaxies like this imply that MOND might be incorrect. And because of this, there's been a kind of a long discussion now between scientists supporting MOND and scientists supporting the dark matter theory, where some scientists have suggested that maybe we just miscalculated the distance to these different galaxies, and they're actually much closer to us, with motion appearing differently. And another recent study has even suggested that certain galaxies that seem to possess no dark matter could maybe just be observed from a very different angle. Instead of looking at them face on, we might be just looking at them from a slightly shifted angle where motion appears differently. Oh, and by the way, quick clarification, when we're talking about motion, in this case the scientists are actually measuring the motion of different globular clusters that are orbiting around these galaxies. These objects are pretty bright and they're quite easily visible from millions of light years away from us, so that's what they're really talking about. Although in some cases they also measure the motion of the actual dust inside the galaxies, but usually it's globular clusters. But more importantly, a lot of astronomers today believe that galaxies cannot form without some kind of a presence of dark matter. As a matter of fact, dark matter is believed to be the foundation for the formation of galaxies in what you're observing right here, in the cosmic web. And so it's the cosmic web in this case that's responsible for more or less creating the galaxies we're observing across the universe. And the cosmic web seems to be produced by the mysterious dark matter. At least that's one of the most accepted explanations. But when the scientists discovered DF2 and DF4, which seem to be relatively close to one another, this was kind of strange. And so here the scientists behind the original discovery started to speculate maybe there's actually more. Maybe there's an entire trail of these unusual galaxies which might have been created in a very unique way. Moreover, when it comes to the type of these galaxies, there are already so many unanswered questions. So these galaxies are generally known as the ultra-diffuse galaxies, or UDGs for short. Unlike a typical dwarf galaxy like this one right here, known as Small Magellanic Cloud, a typical UDG is defined by an extremely low brightness. Mostly because there are not a lot of stars, but there is quite a lot of mass here nevertheless, usually through the presence of different types of gas, and potentially a lot of other massive objects as well, maybe black holes, maybe something else. But the strangest thing about UDGs is how different they are even within this class itself. Some of them seem to possess ridiculous amounts of mass. A good example here is the galaxy you see on the screen known as Dragonfly 44. Its mass is huge. It's essentially just a little bit less massive than our own galaxy, the Milky Way. Once again determined by measuring various globular clusters. But its luminosity and overall look, I guess, is very similar to those other galaxies I showed you that don't have any dark matter. And their mass is ridiculously small in comparison. So in this sense, it doesn't really make sense how some of these galaxies have huge amounts of dark matter, almost entirely made out of it as a matter of fact, and some galaxies seem to have none. And it looks like, in this paper, the scientists might have found one good explanation with visual confirmation of what they're actually looking at. So what exactly is this and what does all of this mean? In this new paper, the astronomers realized that there seems to be some kind of a line of at least 11 different ultra-diffuse galaxies that don't actually contain any dark matter in them. And all of them might have been created in a very similar way. They were probably formed as a result of some kind of a massive collision between two different galaxies. One of them is that bigger galaxy known as NGC 1052, a relatively large elliptical galaxy located in the vicinity of the two smaller ones, and some kind of a smaller progenitor galaxy which could have actually become the remnant known as DF7, with the more exact steps defined in these images. So here we have two different galaxies with both dark matter and gas in them. The galaxies that upon their collision start to intermix, with some of the matter, including old stars and old globular clusters, being thrown out to the outskirts, along with, as you can see, dark matter. And because this was a head-on collision and very high-speed collision, the dark matter and various stars would have sailed past each other without any star interaction or collision, with the gas and the stars eventually slowing down, becoming more compact, and eventually forming new galaxies as a result. But the new galaxies did not contain any more dark matter because all of it was initially thrown away. And since this scenario connects the two galaxies we've discovered so far, along with potential other discoveries, and even connects them to the larger NGC 1052, at the moment this seems to be one of the better explanations out there, with all of this most likely happening approximately 8 billion years ago. But more importantly, all of this also forming other structures. Structures that could be found in future studies. At the moment this is of course a hypothesis, but by looking around this region and along this line, the future studies might be able to confirm this and more importantly discover some other unusual features we've never seen before or have never thought about, with some of these other galaxies potentially being some of the initial targets for the investigation. And so because at the moment there seem to be at least 3 to maybe even 7 dark matter-free galaxies along this particular line, with 2 very strange faint galaxies at the end of the line as well, which as this image shows could be the actual dark matter and remaining material from the original collision, at the moment all of this presents a really interesting scenario that definitely has to be confirmed, that could actually provide us with a really good explanation for everything. And because both DF2 and DF4 galaxies are also relatively stable and also seem to be very different from other dark matter-free galaxies which most likely were created relatively recently, and most likely because of the interaction with much more massive neighbor, at the moment a collision 8 billion years ago is really the only possible and feasible explanation here. And naturally, if all of this is correct, it can also help scientists figure out how exactly dark matter behaves when galaxies collide. Once again, possibly even help scientists to figure out what dark matter actually is by looking at those two individual galaxies on the outskirts, and could also answer a lot of other questions in regards to various galactic collisions and what happens to various material in those galaxies when two galaxies collide at high speeds head-on. Although at the moment it really only explains the formation of these two unusual galaxies, DF2 and DF4, not really other galaxies we've discovered that don't possess dark matter in them. There are still some other ones which are unexplained even today. But it will probably take some time, possibly a few months, maybe even a few years, before the scientists can confirm and, well, most importantly calculate the distances and the masses to all of these galaxies observed in this picture, and thus establish what's actually happening here and if the hypothesis is correct. It is a very exciting explanation, but it could be also completely wrong. For example, if a lot of these galaxies are not on the same line, and if they're actually much closer or much farther away from us, this kind of invalidates this entire explanation. But because this is the best explanation we have so far, I'm actually kind of excited to talk about this in some of the future videos as the new studies come out and as new explanations become available. Hello wonderful person, this is Anton, and today we're going to be discussing some of the new potential resolutions to one of the mysteries of the universe. The mystery that was officially discovered only a few years ago by the New Horizons probe. The mystery related to the darkness of the universe itself. And more specifically, if we were to actually zoom in right here, focusing on some of the darkest spots in the universe, we'll start seeing a lot of background light. And some of the observations of this light from the New Horizons probe don't actually make sense. And so for the past few years, some of the scientists have been trying to resolve this with this new intriguing study that you can find in the description below, proposing a new explanation. Maybe it's actually because of dark matter. But anyway, let's take a few steps back and let's start with the discovery and the probe itself. New Horizons probe is of course one of the most important and most successful missions launched by NASA in the last decade or so. It took some incredible pictures of all of the objects it passed close to, and most importantly, it took some of the most incredible pictures of Pluto, Charon, and even more distant objects as well. The discoveries from Pluto alone were absolutely mind-blowing. And you can obviously find more about all of this in one of the previous videos in the description. But its mission is still not over. As a matter of fact, it's still doing a lot of science. And some of its science is currently done by basically trying to look at things where nobody has looked before. And since this probe has one of the most sensitive and most accurate cameras produced at that time, and is also currently located really far away from planet Earth, you can see where it is right now, right here. It's about 55.5 astronomical units away from planet Earth. It essentially means that we can use this opportunity to start looking at various objects from the edge of the solar system. And so a few years ago, someone had a brilliant idea. Let's point this at one of the darker spots we have, and then try to see what comes out of this. And so here's one of the papers from 2017 announcing some of these results and some of these observations. But what could you possibly see if you looked at these dark areas? Well, because this camera is not really a telescope, it's not going to be seeing distant galaxies. It's mostly going to be seeing darkness, but it's still going to be seeing some background light, of which there are actually many different types. The most famous type of background light is what's known as CMB, the cosmic microwave background that sort of looks like this. But this you can only see in the microwave light, or microwave frequencies. New Horizons doesn't really have that or is not interested in seeing this. But there are other frequencies of light that can be observed by observing empty space. We obviously have X-ray gamma ray light, but in this case there is also optical light, or essentially light that we should be able to see with our own eyes. And about 6 years ago we did have a prediction for how much of it should be detected if seen by various telescopes or various cameras. Now, because most of these measurements previously have been done by the Hubble telescope, that's actually located very close to planet Earth, which means that it's not in the darkest possible place to observe this, a lot of the observations from Hubble because of this were not super accurate. But New Horizons was in a dark place, so its observations would be more accurate. and the observations were at least twice different from what was predicted. The background light was twice brighter, which back then meant several things. The first obvious explanation was that maybe there are just a lot more stars and a lot more galaxies out there. Maybe our estimates were wrong, and a lot of this optical background radiation is actually produced by many different types of stars that we're not seeing, or didn't even know existed. But if so, it would create a lot of other problems for a lot of other theories. If there are way more galaxies and stars out there than we actually see or even predicted, well, that's not really an explanation. That just creates another problem. How do you explain that? And because we're not really seeing that many near us, it didn't really sit well with a lot of scientists. And so there were obviously other explanations. But now we have this really intriguing one that doesn't actually create more problems, but potentially solves a problem. It does, of course, involve dark matter. And the explanation is really simple. If there is a hypothetical particle known as axion, with an extremely specific mass determined in this paper, in the presence of very powerful magnetic fields, it would then decay into a pair of photons, producing the light we're observing. But the thing is, none of this is a new proposition or a new solution. This has been proposed many years ago. As a matter of fact, the original proposition for the existence of axions, the hypothetical particles, was made in the 1970s, and it had nothing to do with dark matter whatsoever. It's actually the most popular solution to one of the biggest mysteries of physics, known as the strong CP problem. Now, I've actually explained this in one of the older videos that you can probably find somewhere in the description, and it does require possibly a few minutes to explain, actually quite a lot of minutes. But in a nutshell, it's a problem with particle physics, and specifically quantum chromodynamics, where the actual observations we're seeing from how matter is in the universe doesn't really make sense, unless there is something else going on with hypothetical particles, such as axions for example, that can actually explain what we're seeing. And so trying to figure out if axions exist and what mass they have has been a problem in physics for many years, and it was a problem that had nothing to do with dark matter. In this case, the scientists were really trying to solve one of the older mysteries in physics of why the universe and the matter in the universe is the way it is. But, as a kind of a side note, someone proposed that maybe, if axions do exist, they could also explain the mysterious dark matter, and a lot of the observations and a lot of the mathematics behind it kind of made sense. And so basically, if axions were real, and if they had very specific masses, they would actually solve two mysteries at the same time. The mystery of dark matter and not seeing dark matter, but also the mystery of why particles are the way they are. But powerful magnetic fields should still be able to reveal them, and so a lot of studies have been trying to find them around black holes, neutron stars, or even our own sun, but so far obviously nothing. And this is kind of what this paper is trying to explain or trying to tackle. It actually suggests that all of this extra light, or basically twice as much as we expected, could really be coming from very specific types of axions all over the universe, being annihilated by magnetic fields in the universe and then creating light. And since they make an actual physical prediction for their mass, 8 to 20 electron volts, it gives other studies and other scientists a reason to prove or disprove this, because this is a mass that was never looked at. In this case, the mass proposed is much lighter than a lot of other predictions, and none of the dark matter or axion detectors have never tried to find particles of this mass. Okay, not entirely correct. Xenon NT experiment, which is an upgrade of an older Xenon experiment, can potentially detect them, but it's only started operating very recently, and there haven't been any major releases just yet. But more importantly, these initial observations from New Horizons now kind of give a reason to try this with a lot of other observatories, focusing on the same type of light and similar detections. These future experiments that are known as the line intensity mapping, that you can actually learn more about in one of the papers, kind of involve studying these slices of the universe at different frequencies in order to make new discoveries. And so by doing these at different frequencies and looking at different parts of the universe, and using other instruments such as the ultraviolet detector on the New Horizons, or even gamma ray telescopes we have operating nearby, it might become possible to either detect more of these signals or even find other frequencies of light that could be explained by other types of axions as well, thus potentially proving this idea. But at the moment, it's just a first proposition. We still have no idea if axions are real, we still have no idea what's causing much brighter optical background light, and we still have no idea if dark matter is even real. But maybe within the next decade, we'll have some of these answers from some of the future studies. Hello wonderful person, this is Anton, and today we're going to be discussing some of the new discoveries in regards to the mysterious dark matter. and more specifically, a potentially really good explanation for why in the last few years the scientists have been finding certain galaxies that don't seem to have any dark matter, with the explanation providing evidence for how those galaxies are made. But in this case, we are obviously working off the assumption that dark matter itself, the phenomenon that we refer to as dark matter, seems to be some sort of a particle or some sort of actual matter, not a phenomenon caused in our misunderstanding of the gravity, or the phenomenon that can be explained by modifying certain formula, which is of course not something that has been proven yet. As a matter of fact, this is one of the biggest mysteries of the universe. The effects of dark matter are visible everywhere, even in certain really massive galactic clusters like the famous Coma cluster, but what causes it is not known. So anyway, in this case, I wanted to actually start the story with the mystery itself, and this only started back in 2018. It started with this unusual galaxy that you can barely see in this image from NASA. It's known as NGC 1052 DF2, and we've discussed this galaxy many times before. But it also seems to have a relatively close neighbor that also seems to look very similar to the galaxy. That particular galaxy is known as DF4, and to everyone's surprise, when the scientists originally found these galaxies, unlike your typical diffuse galaxy or a typical dwarf galaxy, these two galaxies seem to possess practically no dark matter whatsoever. Now, how do we know this? And that's actually important to understand. The way that the scientists study this today is by looking at the motion of various objects in a galaxy, something that's often referred to as the galactic rotation curves. Now, in a galaxy that possesses dark matter, we usually see something that you see on the right side. All of the stars here generally have the same velocity, even though logically you would expect the stars on the outskirts to move a little bit slower, just like planets do in our solar system. This doesn't happen. They move pretty fast. But with these two diffuse galaxies, when the scientists looked at them, they realized that the stars in those galaxies were doing something different. They were doing something that's similar to the left side, moving way slower than they should, suggesting that the total mass of the galaxy was extremely low, way lower than it should be if it does have any dark matter in it whatsoever. And by the way, here they're not actually measuring stars, they actually measure the velocity of so-called globular clusters. So basically objects like this that you see right here next to our own galaxy. And these are, because they're so bright, are extremely easily visible even from far away. And so several different explanations were given for this, and many explanations kind of at first made sense. But one of the more recent explanations involved the idea of nearby large galaxy known as NGS 1052, with the galaxy somehow responsible for the absence of dark matter inside these two. Then, just a few months ago, the scientists started to discover even more galaxies that don't seem to possess any dark matter, with the most recent discovery being the galaxy you see right here, known as AGC 114905. It doesn't actually look that green, this is just a representation of hydrogen gas in this galaxy, whereas the stars appear in blue, but once again, no dark matter present in this galaxy either, and there were actually 6 more galaxies discovered not so long ago. And so all of these galaxies together now sort of present a mystery. What exactly is happening here? Specifically because when it comes to these small diffuse galaxies, the original proposition has always been that they should be actually more enriched in dark matter. As a matter of fact, by mass, they should actually have way more dark matter than we see in these galaxies, which is normally the case with most diffuse and dwarf galaxies, just not these ones. And so some of the initial explanations were basically in regards to, okay, maybe we just miscalculated, maybe the distance here is wrong, maybe the actual velocity is wrong, or maybe the observations themselves are just wrong. And so many scientists try to confirm this, and every study so far has confirmed the original observations. These galaxies seem to be exactly where the original paper suggested they are, and everything seems to be as originally suggested. And this implied that maybe our understanding of how the universe itself works were just incorrect. Maybe dark matter is not exactly what we think, or maybe something here is just completely broken in terms of our physics. But obviously nobody wanted that explanation. And so some of the recent studies decided to obviously explore this more, but this time using computer simulations. In this case, simulating the evolution of a small piece of the universe that was approximately 60 million light years across, but focusing on approximately 13.8 billion years of evolution, basically from the beginning of the Big Bang until now. There are quite a lot of these simulations that you can actually find for free on the web already, with the famous one known as the Illustris project. But when they started this project, they didn't really expect a lot of galactic collisions and a lot of other things that they eventually observed. And having run the simulations, the scientists found 7 extremely intriguing galaxies that they gave relatively funky names. The names like deer, blue, bird, long hair, and the ones you see in this image right here, with my favorite being the wild potato. And, to their surprise, all of these galaxies were devoid of dark matter, just like the ones that were discovered in the last few years. But where did it go? Their simulation revealed that it was actually due to the galactic collisions with nearby galaxies that were at least 1,000 times more massive, with the dark matter itself being stripped from those smaller galaxies through the interaction with these larger giants, which, by the way, was the conclusion with the missing dark matter in these 2 galaxies. Here, the nearby galaxy known as NGC 1052 and possibly its partner 1054 might have actually stripped these galaxies, with the dark matter disappearing somewhere in the middle. If you'd like to learn more, the video about this is somewhere right there or in the description below. And more interestingly, all of this only took a few passages close to a galaxy or a few near collisions. So basically all of this was extremely fast in terms of cosmological time. And it seems to be pretty common next to large galaxies, which also suggests that we should be finding more of these in the next few years. But more importantly, this does not require any modification to modern physics, to anything that we've seen so far, but also once again suggests that dark matter might actually be some sort of a particle after all. We just have no idea what kind of a particle and what to even look for. And that's essentially because the galaxies that were discovered in this study depended on the idea of dark matter in order to be created in the way that they were formed. With the next really important step being the idea of possibly finding a massive galaxy somewhere out there that's actually actively stripping dark matter away from a smaller partner. This would be a definitive proof of this particular proposition. And I guess the other proof here would be to see how many we can find in the next few years, to see if the simulation created the correct number of these galaxies compared to how many we believe exist out there. Although here it's also important to take a look at some other studies that have presented some other evidence about potential changes to dark matter over the years. Here once again we're talking about cosmological years. And here it relates to at least one study that tried to see how the galaxies and dark matter in those galaxies changed in the last few billions of years. In this particular case, the scientists in the study compared the mass distribution of galaxies really far away, approximately 7 billion years old, to some of the younger galaxies closer to us. In this case, taking a look at nearly 300 different galaxies out there. And by looking at approximately 300 different galaxies out there, they did discover a somewhat unusual pattern that's somewhat difficult to explain. It looks like in the beginning, so approximately 6.5 billion years ago, the so-called dark matter halo used to be much more concentrated closer to the center of the galaxy. And so even though today we believe it might look something like this, in the past it might have been much more concentrated and in effect much smaller as well. But it also had a relatively large region where the density was more or less the same. But second of all, created 2 different regions of density, with one being referred to as the core and one being the halo. And in this case, the scientists imply one thing. They imply that it cannot be explained if dark matter did not interact with other particles, which is basically the principles we believe today, where we think dark matter just doesn't interact with anything. In this case, the scientists imply that there has to have been some sort of an interaction with possibly protons, electrons, neutrons, to actually create what they're observing. Or at least there was in the past in order to create what we're seeing. And so here something might have changed over time and the dark matter might have evolved somehow. So basically yet another mystery to deal with for some of the future studies. And so here they believe that it's very likely that the dark matter was as we predicted in the beginning of the universe, but over time it started to interact with various particles and sort of spread across a larger area, forming the actual density we observe in the nearby galaxies. Once again suggesting that the distribution could be different depending on what part of the universe you're looking at. Or in other words, nobody knows.
In the last few months, ever since the James Webb Space Telescope became operational, there's been quite a few unusual and somewhat intriguing discoveries, coming from really distant parts of the observable universe, with the biggest discoveries being various galaxies that were discovered to exist in very early universe, possibly about a few 100 million years after the Big Bang. With a lot of these discoveries of these various galaxies raising really big questions, with I guess the biggest question being, how could they possibly exist so early in the universe, or how could they form so quickly? I know there are some explanations, and certain explanations do involve possible miscalculations of computer simulations from before, the explanation that you can learn more about in one of the videos in the description. There are also other explanations involving more exotic things, or involving hypothetical ideas that have always been proposed but never really proven, mostly because some of those ideas are just really difficult to confirm through observational science. And in this video we're going to be discussing one of these propositions and one of these potential explanations that to some extent does kind of make sense, assuming that you accept something for granted. Here we have to accept the existence of dark matter as some kind of a particle that's able to interact with other particles through gravitational forces, but also a particle that can sometimes self-annihilate, producing energy that's released in certain frequencies. And so what exactly are we talking about? Hello wonderful person, this is Anton, and today we're going to discuss this very intriguing recent paper that was just published not so long ago that asks a very interesting question. Is there any chance that certain detections from the James Webb Space Telescope are not actually galaxies? Can they be something entirely different, in this case, supermassive dark stars? Unusual objects that would combine dark matter and regular matter and would produce very specific effects visible from really far away. But also hypothetical objects that are not really far off from current explanations of modern physics. In essence, they would contain a lot of dark matter in the center, surrounded by a lot of gas. So nothing too unusual, nothing too hypothetical, but if these dark stars are confirmed, it could once and for all prove the existence of dark matter. And so let's discuss this particular proposition and this paper in a little bit more detail, but let's start with what exactly these dark matter stars would actually be. And first of all, it really all depends on the interpretation of dark matter as a particle. So first of all, this is not to be confused with any kind of a black hole or similar phenomena involving singularity. Second of all, it kind of really depends on the interpretation of dark matter. Here it has to be a particle that's able to self-annihilate, producing energy, but a particle that doesn't interact with anything except for through gravitational forces. So most likely not an axion, but possibly something related to a neutrino or another relatively low in mass particle. At the same time, for the most part, even though there is a lot of dark matter on the inside, these objects would also contain quite a lot of regular gas, hydrogen, helium, or possibly even something else. But in this case, because of the dark matter chunk in the middle, and because of a lot of gravitational forces from nearby dark matter, none of this hydrogen or helium would achieve dense enough states to produce fusion. In other words, it would still be there, producing a really large cloud, but this cloud would be more or less low in density, not able to create anything other than a large nebula, possibly resembling something like this. But the actual light produced here is not the result of fusion, and also not the result of friction, which is usually what happens around supermassive black holes. Instead, it actually is the result of dark matter interaction close to the center, with all of the heat and all of the emissions produced via annihilation. Something that would happen as a result of various dark matter particles interacting very close to one another, releasing very large amounts of heat as a result of very compact and very dense chunks in the middle. But because of this heat coming from the annihilation, it would force a lot of other gas, such as hydrogen, to sort of stay on the outskirts and thus prevent collapse or formation of any star-like objects. But in this case, these objects would be very unique. Unlike stars that would be much smaller, or galaxies that would be much bigger, this would be somewhere in between. The gas cloud would be anywhere from 4 to maybe 2000 astronomical units across, making these objects relatively small in size, less than 1 light year, and of course making these objects appear as a kind of a point source from ridiculously far away distances. But they would also possess ridiculously high surface temperatures and very high luminosity, and especially a lot of gamma rays or high energy particles resulting from the annihilation of dark matter, but also eventually disappearing with time, potentially becoming something else entirely. As a matter of fact, modern theories suggest that none of these objects would very likely exist today, and if they do exist, they would be practically invisible and much lower in density, only detectable through various emissions of gamma rays and the presence of the gas around them. And so the question here is, how exactly did the study here connect all of these observations from the James Webb with many of these hypothetical propositions? Well, this is where it gets a little bit interesting. It's actually in regards to this particular galaxy that's currently believed to be the farthest confirmed galaxy ever discovered, at the redshift of 13.2. And what's intriguing about this galaxy is its unusual point source origin, with the other two galaxies visible in this image right here. All of these galaxies very likely existed when the universe was anywhere from 320 to possibly 450 million years old. But even though they all resemble an unusual red point, or basically suggest that these are point sources, it's really their overall brightness that makes them somewhat unusual. It basically implies an extremely powerful star formation if these are stars, but also something that seems to be happening in a very compact volume of space. And early on, these galaxies were exciting as a potential source to discover first stars, so-called population 3 stars. The first stars that must have ignited the universe and very likely were responsible for the formation of everything else around us. Today it's actually believed that some of these stars could have become extremely massive, up to 10,000 solar masses. And so the discovery of these galaxies provided a potential source for their search. But when it comes to first stars, there was always that other theory, the theory of dark stars, or dark matter stars. And so actually in modern cosmology, there are two potential types for first stars. Either population 3 stars, consisting of hydrogen and helium, reaching enormous masses and exploding as powerful supernova, possibly only thousands of years after, and we actually only have hints of their existence as reported in the video in the description, or something similar to a dark matter star, something that we understand even less. Both are technically possible, and both could even coexist, but as of this year, there was just not enough evidence. But the unusual fact that they were just too bright and seemed to be really small in size made these somewhat unusual discoveries. But I guess the question is, so what evidence does this paper provide for these being something more unusual, like dark matter stars, and not your regular stars? Now at the moment there's not a lot of evidence, but the evidence that is here is kind of exciting. First of all, when it comes to population 2, population 3 stars, when looking at the absorption spectrum coming from these galaxies, it should be similar to other distant galaxies we've discovered so far, including the Lyman break you see right there. But if these are dark matter stars, or dark stars, because of the amount of helium around them, they're also going to have a separate absorption spectrum, helium-2 spectrum, that would be absent in a typical galaxy. And that's mostly because they basically contain a lot of hydrogen and helium around them, which would create two different absorption lines. And what's intriguing is that this was actually proposed back in the days, back in 2011, when the James Webb telescope was still being planned, and basically about 10 years before its official launch. Here the scientists proposed that if we actually do find these hypothetical early dark stars, they're most likely going to contain these unusual helium-2 absorption spectra. And while the preliminary analysis from this paper kind of suggests that they might be there. In other words, it suggests that these unusual 3-point sources also seem to contain definitive signs of not actually being galaxies, but instead being dark stars. Objects potentially 1 million solar masses in mass, at least according to their current luminosity, but as a result of dark matter, producing a luminosity of billions of suns, and also being roughly around 10,000 solar radii in radius. So basically still being relatively small compared to a typical galaxy, much larger than a typical star, but also way more luminous and way more massive. Although unfortunately, at the moment, that's really the only evidence we have. But the scientists in this paper does suggest additional evidence that we can actually discover with further observations using other telescopes. For example, their spectrum should be very different in certain wavelengths, especially approximately 5 micrometer wavelengths. These are not wavelengths the James Webb was able to see. We'd basically need to use some kind of a radio telescope for that. Likewise, trying to create an even more detailed image of this, and potentially seeing a little bit more detail in terms of size, might help us determine if these are point sources or something similar to a typical early galaxy. And because of the amount of observations so far and extreme distances, we don't actually have this information just yet. But this is still a very intriguing proposition with very intriguing observations. And even if one of these objects is proven to be a dark star, it will dramatically change modern cosmology. Okay, I guess not really. It will provide important evidence for the modern cosmology, once and for all showing us that dark matter is definitely out there as a kind of a particle. And in some cases, these particles can even create
very unusual dark star objects. Something that would be very difficult to explain otherwise, but it's still very early to tell. Despite these being point sources, they could still just be really small, super active galaxies, very different from anything else we expect. Although in this case, explaining the helium absorption line is still kind of challenging. Nevertheless, these are definitely exciting times, and will most likely lead to incredible discoveries in the next few years. Scientifically speaking, we're still scratching the surface when it comes to various mysteries of the universe. We've discovered so many things that we didn't know existed only in the last few years. And this of course also applies to some of the more obvious objects, such as stars. Today, the scientists believe there are a lot of different exotic stars out there, we just haven't really found enough proof to definitively say if they truly exist out there. For example, the mysterious boson stars that exist theoretically but haven't really been discovered yet, the mysterious quark stars, the stars made entirely out of quarks and nothing else, the stars that are basically almost black holes but are still surviving and maintaining their shape, and even some weird multi-stars such as the Thorne-Zitkal objects, the stars I've discussed in one of the videos you can find in the description about 5 years ago, although I should probably make a new video about this just to give you some more updates about what we know about them today, which by the way means that maybe you should subscribe if you'd like to learn more about this in the future. Anyway, so yeah, there are quite a lot of different exotic stars. But one of the more interesting stars that we think might exist and might actually prove something else as a result is a type of a star the scientists sometimes refer to as the dark star or dark matter star. A star that by definition could obviously prove the existence of dark matter, and the type of a star that a lot of scientists believe, if dark matter is real, might have existed billions and billions of years ago pretty much everywhere in the universe. And so today we're going to discuss this new study and some of the new updates about this unusual theory, or I guess about this unusual hypothesis, and also talk a little bit more about what we know and what we don't know about these objects. But first, I guess the obvious. This idea implies that dark matter is real and very likely consists of some kind of a particle that we just cannot detect yet. If the particle is real, it's probably something that doesn't interact with matter, doesn't interact with light, and possibly does not interact with itself either. Now it might sound unusual, but we do know that, for example, even neutrinos that took years and years to discover don't really interact with a lot of stuff. They barely interact with anything. And so it wouldn't be unusual for dark matter to also be some kind of a non-interacting particle that just seems to kind of exist and gravitationally influence things, but doesn't really do anything else. Although, as a side note, as of today, all of the experiments trying to find dark matter so far have failed, with only some experiments showing some promise that hasn't really been recreated yet. So we don't know if it's real. But if it is real, at least some of the models in the past have suggested that dark matter could have also possibly changed its effects, or maybe even can interact with something. Specifically, scientists believe that maybe it can interact with itself to some extent. In other words, it can be a kind of a self-annihilating particle. A particle that's essentially its own antiparticle that then annihilates, creating energy. And it could still even be doing this today, and this could be one of the ways we can discover this dark matter by looking at certain regions with higher density where it could be producing certain types of energy. Now in the past, some of the scientists have actually tried to explain the mysterious gamma ray glow, detectable from the center of our own galaxy, as potentially higher density of dark matter that's expected in this region, annihilating and creating certain gamma rays. Although at least one recent video suggested that it could also be pulsars, with pulsars currently being the most likely explanation. Either way though, in modern universe, the concentration and the density of dark matter would just be too low to produce a lot of these observable effects. Mostly because modern theories predict that dark matter is very likely in a kind of a halo-like formation around a typical galaxy, with most of the effects produced by this halo observable across the universe, and there are actually quite a lot of effects we've discussed in some of the previous videos. At the moment there's really no better explanation for what's happening here. But the thing is, some of the previous experiments that try to simulate the universe by using supercomputers determined that if dark matter is just this non-interacting particle, it doesn't really necessarily recreate the exactly same universe as we're observing. It still sort of looks like our universe, but it does have certain properties that don't add up. Specifically, the galaxies end up being a little bit more compact than usual, and will often have way more galaxies orbiting around them than what we're observing in the universe. However, when the model is changed just a little bit and the dark matter particles become slightly more interacting, this is when we do recreate the universe we seem to be observing. In other words, this very weak self-interaction could be really important for the formation of the universe as we know it. And this is of course where the suggestions from this new paper come in as well. If the dark matter particle is slightly self-interacting, at least in theory, it could also not just produce the universe as we know it, but it could also produce certain types of stars that might not exist anymore, but could have existed a long time ago. And this is where this idea of dark stars or dark matter stars comes in. They're not truly made of dark matter, but they possess a lot of dark matter on the inside. But from the outside, it would sort of resemble a typical gas cloud, containing a lot of hydrogen and a lot of helium. And because the early universe was also obviously a little bit more hot and a lot more dense, chances for these particles to come closer together and produce denser objects was a lot higher as well. And so as a result, it could produce these relatively large, somewhat compact but not too compact clouds, possibly a few thousand astronomical units in size, maybe even up to about 1 light year across. Inside of this cloud, there is quite a lot of hydrogen and helium, but also quite a lot of dark matter, mostly concentrated very close to the center. And this is where a lot of the dark matter particles start to essentially self-annihilate and produce a lot of energy. Energy that sort of resembles a typical star energy. But in this case, not really powered by nuclear fusion, instead literally powered by these annihilating dark matter particles. But unlike a typical star, they would not really be easily visible with naked eye. As a matter of fact, they would not really resemble a star at all. I guess calling them a dark star is quite appropriate. Instead, they would very likely emit a lot of gamma rays, a lot of neutrinos, quite a lot of antimatter, but mostly be invisible in a lot of other frequencies. And the only other giveaway sign here would be the presence of huge amounts of gas, specifically a lot of hydrogen gas and quite a lot of helium as well. And so if we do detect a relatively large gas cloud that seems to also possess a lot of very energetic particles coming from within it, that's essentially the presence of some kind of a dark star or dark matter star. And because there will be so much dark matter present inside of these objects, in theory they could continuously produce energy for at least a few billions of years and even maintain these objects without collapsing them into anything else. In other words, without even needing any kind of nuclear fusion to produce the energy that typical stars produce. And because they technically have no limit, they could also be extremely bright and much larger in size than anything that we have in the modern universe, so much bigger than any star we know of. However, once the dark matter self-annihilates enough, and once the density becomes much lower, that's when the gas might start collapsing into something else and maybe even produce a typical star. And because the density of dark matter would be much lower today, we don't really expect to find anything like this in the vicinity within a few billion light years away from us. However, in this case, the scientists propose that by using telescopes like the James Webb Telescope, we might be able to see far back in time to actually finally detect these stars through the specific observations of hydrogen gas and other very specific emissions. And obviously, if these stars are detected somewhere in the early universe, that will be a giveaway sign that dark matter is real and seems to be some kind of a particle. And also, if these types of stars were real, they could have been responsible for the reionization of the universe, at least in the beginning. In other words, they could have been the first stars that might have served as a template for a lot of other stars later on that eventually formed into galaxies. And so it's a pretty interesting idea, but obviously, for now at least, it's just an idea and just a hypothesis. We don't really know if these stars existed, and obviously we have no idea if dark matter is real either. But years later, if we end up finding something like this, it could explain so much about the early universe, and even explain some other mysteries such as how certain black holes were able to grow so large so quickly. By having these dark stars with a lot of mass inside them, it would be possible for all of this to suddenly collapse into a relatively massive black hole, possibly thousands or even millions masses of the sun. And so at the moment, this is actually one of the better explanations for what we still don't understand about the universe and how things might have been different in this early universe in the first few hundred millions of years. Sometimes I'm really surprised at extremely clever techniques scientists discover in order to study the early universe and in order to actually try to answer some of the questions and tackle some of the mysteries in regards to the various structures that existed in the first few billions of years since the universe began expanding. Especially because some of these really distant objects are practically impossible to detect using modern techniques. Now we have telescopes like James Webb Telescope that's now helping us see some of the things, but it's not helping us see everything. and especially seeing things that are already difficult to see, such as the mysterious dark matter. The unusual phenomenon that we still don't really understand very well, but that seems to be all over the universe. And even today, nobody really knows if it's some kind of an invisible particle that we just have trouble detecting, if it's some kind of a phenomenon involving maybe unusual physics we don't understand, or maybe we just have to change some of the formula, specifically formula in regards to gravity, in order to finally understand what's actually happening in the universe and what exactly dark matter is. Hello wonderful person, this is Anton, and so today we're going to be talking about this new study that actually found a way to detect and to sort of visualize dark matter at extremely far away distances from planet Earth, something that was basically impossible before. But using new, brilliant methods, the scientists found a way. And to some extent this once again proves that something unusual is going on in the universe after all. But more importantly, in this new study you can find in the description below, the scientists once again discovered something that was not expected, something unusual, and something that probably requires explanations in future studies. But baby steps. Let's start with the basics and also with the main problem that scientists currently have. Now, we've actually discussed dark matter and why the scientists believe it's real in one of the previous videos that should be in the description, but in a nutshell, for this video, we're going to assume that there's definitely something going on, and approximately 85% of all matter in the universe seems to be this unusual phenomenon, dark matter. Once again, maybe a particle, maybe something to do with the formula, maybe something entirely different. Currently, nobody knows. But it seems to be real. Something in the universe seems to clump things together and seems to cause things to basically orbit much faster than they should orbit. As a matter of fact, the first image that was released by the James Webb Telescope is essentially a direct proof of the existence of dark matter. You can actually see its effects in the lens produced right here in the middle. Because without this unusual phenomenon, this particular galactic cluster would not be producing these unusual lensing effects to such an extent. The only current way to explain these very powerful lensing effects, if there was something really massive present in this cluster, something that cannot just be explained by gas and the visible stars. Around 85% of mass that's causing these lensing effects is basically invisible. But most of the modern studies in regards to dark matter usually focus on a lot of the observations in the galactic clusters. Or in other words, even though we cannot really see it, we can still detect some of the effects from various observations and calculations of various emissions surrounding typical galaxies. In this case, this is often referred to as the galactic halo. But even though these halos are detectable in some of the nearby galaxies, when it comes to really far away galaxies, it becomes a bit of a problem. To be able to see this really far away, billions of light years away, we would require some ridiculously powerful telescopes we just don't have. As a matter of fact, previously the scientists usually relied on the idea of gravitational lensing effects in order to actually even see any of this. But in order for the gravitational lens to work, you basically have to have some kind of a massive object in front of another object. But what if you're actually trying to measure the properties of some of these most distant galaxies? Galaxies that don't actually have any lenses in front of them. Well, one interesting way of measuring what's happening inside these halos is by, for example, measuring the dispersion frequencies of very distant fast radio bursts, so-called FRBs. At least one recent study realized that you can use approximately 400 or so FRBs coming from various directions and use the dispersion frequencies of these FRBs to actually study the halos of various galaxies. But then again, what if you want to study something even farther away? What if you really want to reach as far back in the observable universe as you can? Well, in this case we have to use some other light. We might have to use the first light in the universe, the cosmic microwave background. But it wasn't until very recently that the Japanese scientists finally figured out how to actually do it. So how did they do this? First, they used some of the brightest galaxies visible in the early universe. These are usually referred to as the Lyman break galaxies. Extremely bright galaxies because they usually form a lot of stars and are also sometimes referred to as the starburst galaxies. And because of this really powerful star formation, they generally produce very specific frequencies of light, with most of the light being related to the spectrum of hydrogen. As a matter of fact, pretty much most of the record holder earliest galaxies so far were detected using this method. And so this is a pretty well-known technique, with a lot of these galaxies in the early universe very often forming very large galactic clusters, with sometimes up to 1,000 galaxies forming a large cluster together, which can then produce huge gravitational effects, and naturally also possess quite a lot of dark matter on the inside. Now, this program right here has actually explored a lot of these galaxies before, and has actually collected approximately 1.5 million of these objects that's accessible from their free survey available in the link in the description. And so for this study, the scientists decided to use various galactic clusters and individual galaxies from the survey, specifically about 1.5 million of these objects, and combine them with the observations from the Planck telescope that collected the data about the earliest light with the cosmic microwave background. And in this case, a lot of these early galaxies, especially in the large galactic clusters, are expected to produce a very brief lensing signal similar to this lens detected in the first image from the James Webb. Although in this case the lens would be a lot more subtle and would be a kind of an imprint left by these high redshift galaxies in the cosmic microwave background itself. And so by combining the microwave background with the location of these high mass galaxies, it sort of becomes possible to work out the average mass distribution around the galaxies that existed about 12 billion years ago in the early universe. In terms of the actual redshift, this represents the redshift of about 4. And as you can imagine, the total mass of all of these galaxies did actually distort some of the early light passing through these galaxies 12 billion years ago, allowing the scientists to estimate the average distribution of dark matter in a lot of these early galaxies, and then also comparing this to some of the earlier models we have on dark matter distribution. In the process discovering that, well, there definitely was some kind of unusual matter present in these early galaxies as well, but it was different from what the scientists originally predicted, suggesting of course that something here does not add up. The matter that was present here was not as clumpy as the scientists originally predicted. Or in other words, the density was much lower and the galaxies were much more spread out. Which does present a bit of a problem because it means that we don't really understand the early universe as well as we thought we did. It basically means that a lot of the dark matter in the early universe, or whatever was happening in the early universe, was acting very different from how the theories predicted it to act, suggesting some kind of a mystery or some kind of a problem with modern models. And though in this case, the scientists do actually admit that maybe it could be because this is the first such study and there could be some problems with calculations, on the other hand, this could also point at that unusual problem we currently have with the so-called Hubble tension that suggests that the universe might have been different in the first few billions of years, in terms of the actual physical properties. For example, some of the constants could have been different from the way that they currently are. Here we're talking about the idea of cosmological constant that you can learn more about in one of the previous videos in the description, or maybe somewhere right there. But that's also where a lot of observations from, for example, James Webb Telescope or from the upcoming Vera Rubin Observatory will help the scientists quite a lot as well, because it will allow the scientists to finally figure out what's actually happening here. At the moment, all of this is a bit of a mystery, actually a big mystery, both in terms of the understanding of what dark matter is, and also in terms of the understanding of what exactly was happening in the early universe to make it so different from how we believed it to be. So many questions to answer and so many mysteries to try to resolve. Hello wonderful person, this is Anton, and today we're going to be talking about the expansion of the universe and the Hubble constant once again. And more specifically, a recent announcement from the team using the Hubble telescope that once again confirmed that there is something strange going on with the rate of the expansion of the universe, with the concept that today we refer to as the Hubble tension. The concept that suggests that the universe seems to be expanding at different rates, and the actual acceleration of the expansion does not currently make any sense. But I guess let's discuss this in a little bit more detail and focus on the idea behind the expansion and also a bit about history of how we know all of this, because I usually get so many questions about this. But I guess the first main question is, how exactly do we even know the age of the universe? Well, we don't really know the age. We sort of estimate the age based on the expansion, with this overall concept of course known as the Big Bang Theory. And to try to understand all of this and the problems generated by this research, we kind of have to start in the early 1900s, because basically for the most of the 20th century, because most of the cosmologists of the 20th century spent all of their time essentially trying to figure out what exactly is happening with the shape, the size, and the age of the universe. But all of this had to be done by measuring the expansion of the universe. And all of this began with the iconic Edwin P. Hubble that you see right here. We've actually discussed this in one of the older videos that should be somewhere right there or in the description, but in a nutshell, about 100 years ago, even though most scientists back then believed that this is pretty much the entire universe, we basically live in this galaxy known as the Milky Way, Hubble realized and helped the scientists see that there were so many other galaxies out there, with many more discovered as the time passed. And as a matter of fact, he also definitively showed that many of these galaxies were very far away, much farther than anyone ever believed. Moreover, as he started to look around the universe, he also realized that many galaxies were not really standing still. Everything was sort of moving. But what was surprising is that the farther the galaxy was, the faster it was moving away from us. And so back then, a lot of scientists agreed that the universe seems to be expanding because that was the only natural explanation. And because it's expanding, it kind of becomes possible to trace back, well, everything. You can kind of move back in time and figure out when all of this started. And so this allowed the scientists to kind of estimate the beginning of the universe, the so-called Big Bang, when everything started to expand. Although even back then, his early observations and early calculations, because of the unusual oddities, already suggested that something strange was going on everywhere. But in order to figure all of this out and in order to understand this, the scientists had to create what's known as the Cosmic Distance Ladder, or basically a kind of a database of different galaxies with their velocity and distance away from us, in order to then try to figure out how fast everything is expanding and how fast everything is moving at very far away distances. But because everything in space is already so far away, this was of course a bit of a challenge. Now, for closer objects we usually use what's known as parallax. But how do you measure distances really far away? Parallax doesn't work anymore. Well, this is where early astronomers, and specifically Hubble once again, figured out that you can actually use two things. You can use supernova, and you can also use a very specific type of a star known as a Cepheid variable. Now for supernova, we know that type 1a supernova generally explodes with a relatively similar energy, mostly because it's a white dwarf that reaches a certain limit of its mass. Now some of the recent studies have actually claimed that maybe this energy does actually vary quite a lot, but that's another story for another day, and that's actually maybe one of the solutions to the so-called Hubble constant problem. But essentially by looking at various supernova out there, and realizing that they generally produce the same type of brightness, you can then start to establish distances across space. Then by looking at the same galaxies where the supernova occurred and finding Cepheid variables, with this being the most famous one known as RS Puppis, the brightest known Cepheid variable in the Milky Way, it becomes possible to place various galaxies on a kind of a distance/velocity scale where we start understanding where they're located and how fast they're moving. And in case you're not familiar with Cepheid variables and what exactly they do, it's a type of a star that seems to have a very specific variation in luminosity depending on its brightness. Or in other words, just like you see right here, these stars tend to blink, but the variation of their blinks directly depends on their mass and their total luminosity, and so there's actually a relationship that allows us to measure distances because of how they blink in the night skies. Something that has previously been used very actively here in the Milky Way to determine distances to very specific objects, including some of the objects in the center of the galaxy. But all of this was very hard work, and many of these galaxies were very difficult to see. And moreover, detecting any kind of a supernova or a Cepheid variable from these distant galaxies became very difficult. And so back in the 90s, NASA launched an incredible mission. This was the birth of the iconic Hubble telescope, naturally named after Edwin Hubble, with the main purpose being the measurement of the expansion of the universe. That was its primary mission from the beginning. But when the telescope was initially launched, the original predictions for example, the age of the universe were very imprecise. It was believed that the universe was anywhere from about 8 billion years old to maybe 20 billion years old, maybe even older. But after the first decade of observations, and after years and years of work, the astronomers finally narrowed down the expansion by looking at various supernovae, and they were able to figure out that the universe is about 13.8 billion years. Also suggesting that the universe might double in size in the next 10 billion years from now. But while doing these observations, something else was discovered in 1998. It was discovered that the universe seems to be even accelerating its expansion, staying really far away are actually expanding much faster than predicted, with this eventually leading to the idea we refer to as dark energy. Something, we don't know what, is causing the universe to expand and to accelerate much faster, with this very likely starting at least 5 to maybe 6 billion years ago. And since then, the idea of so-called Hubble constant was born. The idea that the universe seems to be accelerating its expansion, with several papers trying to then calculate the value for that particular acceleration. Now, by early 2000s, this value might have been found by using various types of Cepheid variables and various types of supernova and the Hubble telescope. So once again, by using a very similar method, and specifically using the Type 1a supernova that were detected several times across several different regions, it was determined that the value for the so-called H0, or the Hubble constant, was roughly around 72 plus minus 8 kilometers per second per megaparsec. Or basically for every million parsec, which is about 3.26 million light years, the universe was expanding approximately 72 kilometers per second faster. Which means that after a billion parsec, this value would be approximately 72,000 kilometers per second. And as you go farther and farther, at some point you reach the velocity of the speed of light. And that's of course where you reach the limit of the observable universe. Everything past that is invisible to us and will never be visible unless some other things happen, such as, for example, the contraction of the universe, but that's another story. So in a nutshell, by using this value of the Hubble constant, H0 as it's known, the scientists were able to figure out that the universe is about 13.8 billion years old, plus minus a few hundred million years or so. But in 2005 and 2009, Hubble received several upgrades, and here the new value was determined once again and was actually closer to about 73 kilometers per second per megaparsec. So far, no problems, everything seems to be good, we might have figured out the Hubble constant. But then other studies using very different observations and also very different telescopes were actually finding something different. The biggest such study was the so-called Planck collaboration that used the observations from the early universe, the observations from the cosmic microwave background. And here we're talking about light that's basically as far back in time as we can see. The universe produced this light when it was only about 380,000 years old, so this was showing us literally the early universe. And interestingly enough, the observations from the cosmic microwave background actually predicted the value to be about 67.5 plus minus 0.5. Okay, let me show it to you in a graph. Over the years, it basically started to look like this. Spitzer telescope and Hubble had the value closer to 73 to 74. Planck had it closer to 67. And notice the error bars, they don't even come close to each other. The chance for an error here was only 1 in a million. And that essentially created this so-called Hubble tension. The problem with not knowing how fast the universe is expanding, and thus how old it is, and obviously how big it is. And with more and more calculations using different methods, using different studies, these particular values did not really change. The scientists mostly found that the values were either closer to about 73 or closer to about 68, 67, or even somewhere between that. And in some cases, certain error bars were not really touching at all. So whatever was going on here has no explanation right now. It could be brand new physics. But more recently, in the last few years, the scientists have also realized that it also seems to be related to the area of measurements. Specifically, the rates in the local universe just seem to be different to the rates in the distant universe, which already implied that maybe the constant is not constant and it actually changed over time or is different depending on the location in a universe, which is already a huge problem because this constant is used in so many different formula and in so many different predictions. On the other hand, the other, I guess, more interesting explanation was in regards to our location in the local group of galaxies. And actually that's the explanation a lot of scientists like right now. They think that maybe it's in regards to what's known as KBC void, a very large void formed by the galactic filament that represents a much lower density and thus much lower amount of stuff on the inside compared to some of the galaxies inside the cosmic web. And so by measuring various objects such as various supernova or various Cepheid variables that seem to be located inside the void, we might be just getting a much larger value for the Hubble constant. And the real value is much lower, with the cosmic web and the voids in between them being responsible for the flow and for the speed of different galaxies around them. Or in other words, because of our position next to this void, we're just basically seeing things moving a little bit differently from things in the outskirts of the universe or in maybe other directions. So this could be one of the potential explanations. Another explanation is, well, different physics. Maybe our models are wrong, and maybe something else is happening in the universe we just don't really understand yet. But to try to finalize these conclusions and to try to figure out if we actually got some of the results wrong, the recent study decided to do this once again. They decided to conduct the most comprehensive and most detailed analysis using some of the recent Hubble data. Data that was collected over a 30-year period with at least 40 different so-called milepost markers, or specific points along the so-called cosmic distance ladder, that allowed the scientists behind the paper right here to once again try to calculate the most accurate value for this so-called Hubble constant. Here are the supernovae used for this particular study and the years when they were actually observed. And some of these supernovae were only observed a few years ago and are actually completely brand new. And these are the galaxies where the supernova occurred and the galaxies to which the distance was measured extremely accurately. And so using this super accurate analysis, the scientists once again determined the value to be very close to 73 km per second per megaparsec, with only a tiny error of 1 km per second. And that once again means that the Hubble tension is definitely real, because the value from the cosmic microwave background is significantly different. And so by using these 42 supernova, the scientists have definitively confirmed that we need to study this even more because nobody really knows what's happening, and even using explanations like the void I previously mentioned might not really explain everything just yet. Many of these galaxies are located in very different regions of space, and so not all of them might be affected by the KBC void, or by being located in a certain region of the cosmic web. So unfortunately, it's not a very satisfactory conclusion, but that's a conclusion they came to very recently using the most up-to-date data. And that of course means that becoming a cosmologist and trying to study this and trying to understand this is a pretty exciting time. We have another mystery nobody knows how to answer, we have another problem with the universe, and because of this we obviously have no idea how old the universe really is, how far away certain objects are from us, or if the modern cosmological theories are even correct to begin with. Hello wonderful person, this is Anton, and today we're going to be discussing some of the new propositions in regards to the idea of dark energy, but also connect all of this to the idea behind the cosmic web and the cosmic voids, the ideas that were recently proposed and explored in one of the recent studies you can find in the description below. But I think first it's kind of important for us to establish what the actual problem is. So when it comes to the universe, in modern cosmology, most of the things in the universe seem to be made out of unexplained stuff, either dark matter or dark energy. Dark matter is responsible for keeping things together and for making things a lot more massive than they should be otherwise. It's still not entirely certain what exactly is creating these effects, but some scientists believe it might be some kind of a particle, some scientists think that maybe it's some kind of a misinterpretation of certain formula. Either way, the effect is real and has been observed several times. But a much larger part of the universe is believed to be dark energy, over 70% in total. And this is a really poorly understood phenomenon, but it seems to cause the universe to not just expand, but to actually accelerate its expansion, making all the galaxies move faster and faster apart from one another. As a matter of fact, pretty much most of the galaxies out there are moving farther and farther away from us. And in one of the previous videos, I've even talked about the few galaxies that are moving toward us and the reasons why they're doing so. The majority of the galaxies out there are not just moving away, but they're actually accelerating away from us. And that's the dark energy in a nutshell. What's actually causing this though is another question. Not a question anyone can answer right now. But within the observable and measurable universe, and here we're talking about the actual matter that we're made from, the baryonic matter, there are also some mysteries here as well. As a matter of fact, if you were to look at the universe from far away, it would sort of resemble this. It would be made out of two main things, voids and what the scientists refer to as walls, with various walls being divided into further filaments, which are the branching arms of various walls, very often millions of light years across, and various clusters where a lot of galaxies and a lot of mass concentrates in large volumes. This is actually also where a lot of walls intersect. And it's actually these cosmic voids that's always been particularly fascinating because they basically look like empty space, with I guess Buta's void and the local void being some of the most popular and most well-known ones. with the Buttes void being particularly well known, but also the local void being the one that seems to influence us the most. As a matter of fact, the Milky Way galaxy is literally right at the edge of the local void. Although a quick side note, these voids are not really empty space, even though they might resemble empty space in this image. In reality, they actually represent just areas of much lesser density, usually about 10% of, for example, a typical cluster. You're still going to find dust, you're still going to find stars and even galaxies in these voids, but they're just not going to be as common. Nevertheless, they do represent the largest structures in the universe, sometimes having a diameter of up to 300 million light-years across, with some of the smallest ones being about 30 million located in the vicinity of the Milky Way. And sometimes when these voids tend to lack any major clusters or superclusters in them, they're also referred to as the supervoids. But once again, they still have some stuff on the inside, just not as much. With the first voids being originally discovered back in 1978 by the scientists from the Kitt Peak National Observatory. And although naturally it's not entirely certain how they were formed, some of the clues about their formation come from the earliest light, the cosmic microwave background. Here, the tiny variations in density formed by various early bubbles following the Big Bang very likely caused the matter to collapse in a very certain way, eventually forming thicker and thicker structures and forming the web itself. Or in other words, even though initially all of the matter was relatively equally distributed, because of various small variations in density, eventually all of the matter started to coalesce into bigger and bigger structures, forming what you see right here, with many different supercomputer simulations being able to recreate some of this and essentially creating something similar to what we actually observe. So this cosmic web, and of course the void between the different filaments of the web, is something most scientists believe definitely exists, with several different studies we've discussed previously even finding actual evidence using various observations. But until this relatively recent paper, the idea of these cosmic voids and the idea of dark energy has never really been connected together, although the scientists behind this paper proposed something relatively interesting. They proposed an explanation for dark energy using these voids, and specifically using the interaction between these voids and the various walls I previously mentioned. So, first of all, when it comes to these voids, because they're mostly empty space, they should technically be affected more by this dark energy and by the expansion of the universe. A typical galaxy or any galactic clusters with a lot of mass should not really be feeling a lot of dark energy effects. In other words, in a typical galactic cluster, the effects from the dark energy are going to be almost invisible. However, in a typical void where the density is much lower and thus there is less mass, the effects should be much more pronounced. On top of this, the analysis today and all of the simulations determined that these voids very likely grew in time and very likely expanded to their current size over the last few billions of years, something that kind of correlates to the appearance of dark energy. Today, the scientists believe that the accelerated expansion of the universe very likely began approximately 5 billion years ago. And so there is a bit of a correlation between the size of these voids and the sudden acceleration of the universe. And so the scientists here propose that there might be a connection, and actually a direct connection. The voids might be pushing things apart, with the scientists behind this paper referring to this idea as a kind of a surface tension of cosmic voids, something that they present in this way. And so as these voids grow larger and larger in size, they actually end up putting a lot of pressure on the walls where the galaxies are located, and kind of forcing them to thin out even more. And here, eventually they might even rip them apart, which will most likely lead to the merger of all of these voids, resulting in even larger supervoids with time, but also dispersing a lot of the galaxies and all of the matter, and destroying the cosmic web in the process. And because this is such an effective process according to these scientists, it will actually take only a few billion years for all of these voids to completely dissolve the cosmic web, eventually creating a bunch of galactic islands, very likely separated from each other by millions of light years, and very likely remaining isolated from everything else for billions of years afterwards, with the surface tension coming from these voids being created by a kind of a distortion of the space-time itself, with all of this sort of being comparable to the effects you can kind of see if you have a bunch of bubbles on the surface of water. All of this pressure generated between the bubbles will eventually make some of them pop or possibly combine into larger bubbles. And the force that's causing all of this to happen can be actually described as a kind of a negative pressure, generated by all of the pressure from between these voids. And so as these bubbles push on each other, they force the galaxies to separate and to form smaller and smaller objects. But more intriguingly, when the scientists crunched the numbers here, their calculations suggested that it actually fits the models of the dark energy. Or more specifically, by adding all of the effects from all of these large voids, the surface tension calculations match the current estimates for dark energy. At least they do to some extent. But because this is the first such proposition, and because this is a very big assumption right now, this will definitely require years and years of observations and analysis before it can be either confirmed or disproven completely. Nevertheless, this idea of negative pressure creating a kind of a surface tension right at the edges where all of the galaxies are located does actually make quite a lot of sense and would be super interesting to investigate in some of the future studies. More importantly, at the moment this is one of the better and more intriguing explanations for what dark energy could be to begin with. And in this case, the scientists even proposed that to some extent this could even maybe explain some of the effects from dark matter as well, at least in smaller scales. And so definitely a super intriguing paper and something I'm looking forward to hearing more about in some of the future studies.